Okay, so you can see here our schedule for today. As I said, I will start out first talking about the calendar, and then Igor will take over, and I'll also talk a little bit about some run deck comparisons, but I won't do very much. I'm just going to point to some online run decks that you can look at. Okay, so he says here Model E, that's really ROCKE-3D. Model E is our parent Earth model, but this calendaring stuff that we needed to put in is in both models. So basically, the idea here is that we have some kind of absolute time in the model that's given in integers, and we have to find a way to basically connect the orbit, which is given in, as it says here, distance, hour angle, and declination angle, and a calendar given in month, days, etc., that correspond to the diagnostics that we output in the model because of our Earth legacy. As you can see here, in our particular model, the exoplanet years are divided into 12 months, or planet years, exoplanets or planets. And the angle, as you see here, is subtended by each month. It's approximately the same as the corresponding month for Earth. So days are subdivided into equal 24 hours. However the long day is, it's divided up into 24 hours. So an hour may not be the exact same number of seconds for a given calendar. And as it says here, sorry, I have to just move this to the bottom. And as Thomas put here a note that the orbital period is adjusted to be an integral multiple of the rotation period for reasons that make things easier to work with. The big issues that we have are basically is that this system that we have works really well when the rotation period of the planet is much faster than the orbital period. But for slowly rotating planets, these assumptions break down. So to get around this this problem, basically, we have set up the calendar such that always, although there's a caveat that always is not always, there are ways to always get around things that we put in, have at least 120 what we call calendar days. And calendar days and solar days are distinct in this classification. I know this sounds very confusing, but don't worry. There are many examples to help you get through this. In a case like this, the monthly averages, as we've written here, may be a bit misleading, and a given longitude may experience daylight for an entire month, even at the equator, as you might imagine. So for very slow rotators, a lot of issues came up when we started doing these projects. And one must deactivate what we call orbit quantization, which means that we have integer values between the orbital period and the rotation period. So if you deactivate this quantization, the seasons can float from calendar year to calendar year, which is something to keep in mind. So an entire calendar year may have kind of a day-night balance, so that when you want to do diagnostics, you really need to run a large number of calendar years to get, as it says here, valid annual averages. And ideally, as we put here again, the least common multiple of orbit year and physical days. So for Venus type simulations where we have a very slow rotating planet, we use at least 50 orbits to get reasonable numbers in a case like that. But if you're confused about that, you just consult us and we'll give you some advice about how to do that. These are the basic orbit run deck parameters. So if you don't put in a planet name and you don't put any of these other quantities I'm going to discuss here very quickly, everything is assumed to be Earth. If you want to use something other than Earth, you have to give the planet some kind of name. So, typically, I think as we discussed yesterday, if you're modeling Proxima Centauri b, call your planet Proxima Centauri b. Although just calling it that doesn't mean that anything is set for Proxima Centauri b. The model is not intelligent enough to do Kepler's laws for you. It assumes you know what Kepler's laws are. And we've even seen papers in the literature, I might add, where people themselves were not very careful about Kepler's laws and put in things that were not realistic. So if you're not sure about these things, consult an astronomy friend. So the basic things to be put in, of course, are things like obliquity, eccentricity. If you don't put these values in, they will always assume modern Earth, even if you've given the planet this planet name designation. Longitude at periapsis. Again, if you don't put that in, default is modern Earth. Typically, for exoplanetary systems, we don't know what the longitude of periapsis is, and we will never probably know what it is. So we just leave it to modern Earth most of the time. But for planets in the solar system, we do know this value, obviously. The sidereal orbital period is given in seconds, and you can see an example here how to do that. And this is automatically adjusted to quantize the year, such that the sidereal orbital period and the sidereal rotation period are integers of each other. Again, in this case, for the sidereal rotation period, the default again is an Earth day. You have to change this to whatever it is that you're interested in modeling. This quantized year length is again such that these two values for the orbital and rotational period are integers. That's set to true by default, but again, if you have a very slowly rotating world, you want to set this to false. So in the case of Venus, you don't want this to be true. In the case for a tidally locked world, you would set the orbital and rotational periods to the same value, and you would set quantized year length to be true, so that these things are fixed, for example. We also have an equation of time calculator, basically. That's basically because the obliquity and the eccentricity have an effect on exactly when noon occurs on a given day. But for Earth, it's a modest effect, plus or minus 15 minutes for a given location. But for resonant orbits, so say 2-3 spin type states like Mercury is in, or maybe some of these exoplanetary systems, this can be a big effect. If you're interested, you can look at some of these descriptions in papers published by Chris Kolos that were mentioned yesterday. The naive option that we've listed here is available for backward compatibility, so that we have run reproducibility, which is very important to our group. And that's the default on the Planet 1.0 branch. But for Planet 2, it's always set up to be on, basically. You probably want on, especially for highly eccentricity planets and that are slow rotators.
I had a quick question.
Yeah, sure.
When you say slow rotator, is there what's the kind of rule of thumb?
Well, yeah, that's a good question. What's the good rule of thumb? I'm not sure that we've quantified this. I would just say leave it on.
Okay.
Only reason that we have these options are for the other options are for backward compatibility.
Right. Oh, but I mean, as far as quantized year length.
Oh, quantized year length.
Yeah, sorry.
Yes, that's a good question. I don't think we've actually quantized. I don't think we've ever quantified this itself either. So I would say, write Tom and myself if you have a question for a given planet. We will give you our best guess. Thank you for your question, Don.
Yeah, I guess it depends on how much you want to allow basically your rotation rate to be distorted to quantize the years. Probably depends on your problem. Sometimes you want like the new year to be sharp at certain point. Sometimes you preserve the rotation rate.
Right, because otherwise you basically, if you have an eccentric orbit, your seasons are going to precess through time. Yeah. So you need to think a little bit like, does that important to me or not?
Right.
Again, in general, in these exoplanetary systems, we don't have super great constraints on the eccentricity. In some cases, we have some constraints, but not great constraints.
So realistically, that quantized year length is to prevent the precession of the seasons.
Yes.
And it's not only that, it's even for the annual means. If you are not having a quantized year, then a single year might be different from the next year. So you have to make climatology over several years to smooth that out.
Right. Okay.
Cool. Exactly right. Finally, there are a couple of rarely used parameters you can set. Mean distance, which is equivalent to basically setting your insolation. If this is what is done on the earth side of the house occasionally. And there's another nice feature that we had to put in for one of our projects called the hour angle offset. That's where you move the prime meridian, which may be necessary if you have a given topography. So for example, the default, if you do a Tally lock system and you give it Earth's topography, the substellar point will end up over the Pacific. But if you want to have the substellar point instead over Asia or Africa, this is where you would set this value to something that shifts it so that the substellar point's sitting over a different part of the planet's topography. Okay, any other questions on this section here? Okay, good. All right, so I put a few things in here that we thought may be useful before I have Igor go on and talk about the land planet hydrology scheme and things like that. These are just exercises for you to consider looking at. So as Kostas showed yesterday, how the P1SOM40 run deck works with the dynamic ocean, you might consider looking at differences between that and, for example, some of our ancient Venus simulations. So, for example, we have an aquaplanet simulation whose run deck you can download directly from this URL that's given on the slide. And for example, the AIC file, in this case, we set the winds to 0 and we set a couple of other values so that the model starts up in a nice way. You can compare things like the ocean bathymetry, the topo OC file, and the ocean initial conditions files in those. And then we have a couple other examples from this 2020 paper, the Venus 310 meter deep ocean, which is simulation 23, as you can see here. And you can see where the river directions file is defined. But as we said yesterday, in Planet 2.0, this river directions file is not required any longer, although you can use it if you want. And then there's an example of a Venus land planet. And then there's one other here that I thought would be very useful to people. That's again on the repository. This is back to our Proxima Centauri B paper from 2018 or 2019 that was led by Tony Del Genio. And again, there's some examples here for an aquaplanet, an Earth topography, and you can also see some information about the particular radiative transfer files that we use, which Eric will talk about a little bit later this morning. And you can see some of these entries that we have for the various parameters. So many of the calendaring things you can see here are defined very clearly. So that could be useful for you all in both of the cases I've shown here. And of course, this planet params _ mod.f90 file, which has entries for Venus in this particular case. Okay, so finally, I think we talked about this yesterday, so I'm not going to go through this again about RSF files. I don't think there's much to say at this point on these things, so we'll move on and let.
Well, I guess we should mention, we didn't discuss iStar.
I thought we would discuss that tomorrow, I think, or we not?
Tomorrow.
Oh, not tomorrow, sorry, later today. Are we discussing the iStart stuff? Maybe not, okay. So, yeah, maybe we should mention this thing very quickly. So we mentioned that you can output these checkpoint restart files as often as you feel is necessary. We don't recommend you output them every month because they take up a lot of disk space and they will also start killing your input output. But if you're going to use one of these RSF files to restart or run, there are two options that you also need to put in. So first of all, you put the path to the restart file that you want to use for your new run. And then you have to set the iStart value at the bottom of the run deck to either 9, which would continue exactly the same run as before, or 8, if you want to start a new run, but it also resets the ground hydrology
if you want,
conditions if you want.
and you have a choice to do that or not.
Right. What's the option for not setting it? I've forgotten that.
It's there are a couple of things that you can modify in the run deck for that. So there is a way to make iStart 8 to be exactly equal as iStart 9 in terms of functionality.
Right.
The reason why 8 exists, I mean, there are a number of reasons, but one of the things that for iStart 8 is that you can modify the date.
Yes.
So if you, for example, you are saving for whatever reason you want to restart from 1 or skip years or whatever, then you can do that with iStart 8. You cannot do that with iStart 9.
iStart 9 continues literally from the end of the
iStart 9 is supposed to be an exact continuation of the same configuration that the restart file came from. iStart 8 allows a little bit more flexibility in changing some things if you want or not.
You want to add something, Igor?
Yeah, one important thing about both restarts is that it is used basically the same orbital parameters. So if you want to use restart file from a run which has slightly different orbital parameters, then most likely it will not work, and we need to apply some hack, which I don't think we describe in the documentation, but you can email us.
You can email us.
We will tell you what to do. It's simple, but basically, model always checks the time of the year of restart file and would not allow you to restart from incompatible restart file. So it's done for your own good, but sometimes.
But you can insist.
Yeah.
And
Yeah.
So to change orbital parameters, you have to use 8? Is that what you're saying?
It doesn't
8
matter,
plus-
but 8 is, I guess, safer, but you also need to reset time manually in the restart file. And that's
And we can tell you how to do that,
Yeah.
but it's not
Yeah.
trivial. I mean, it's trivial, but we have to show you.
And
Yes.
so you need to start a restart run back from the run deck. You can't modify the I file. You have to recompile the run deck.
You can modify some things in the I file.
Yeah, you can modify, I guess, most things. But
Yeah, you can modify the insulation, you can modify, if you want to use different radiative transfer files, you can modify those.
Yeah, you should modify, of course, orbital parameters.
Yes, as you just said.
And you cannot modify the main physics study step. But when you restart from iStarticle 8, you can modify basically everything. So except if you modify orbital parameters, then there is some hack.
So could you start a restart run from just changing the I file, or you have to?
It is safer to basically to create new run back and
there is a thing. If you modify the I file, you continue an existing run. You cannot create a new run, because then if you create a new run with a new run name or run ID, there is no I file. You have to make setup. And in order to make setup, you need an iStart value. But for continuation of a run that you modify the I file, the model will not look at the iStart because it will not run the setup hour again.
It just depends on if you want to do a new run or you want to continue that existing run, basically.
Okay, so if you wanted to continue an existing run, you could just use that.
Modify the I file and you just move on, yeah.
And the end, the time is possible to change it.
You can change,
Yeah,
Yeah,
you
you
can always-
can change that in time. Yeah.
you can always change it in the I file. Yeah,
Yeah,
because you might have run 1,000 orbits and
Yeah.
decided it's not in equilibrium, so I'm going to change the year E to 2,000. Maybe I run another 1,000 orbits to see if I get into equilibrium.
And something that is really a minor thing, but it's convenient. As the model runs, I hope that everybody is checking how the model is going. You don't expect the model to finish before checking for the first time. So as the model runs, if you see that you will not have enough time till year E for whatever you want, and you know before the model finishes that you will need an extension, you can change the I file as the model runs. You don't have to stop it, change the I file and continue. You just do it on the fly.
Oh,
But
no.
it will only be taken into account the next time the job
Yes.
is
Yeah.
submitted, yes.
Yeah.
So you can-
Not
Yeah.
while.
Not while it's
It will
running.
not happen.
while it's
I mean,
Yeah.
if there are 5 minutes before the job stops, it will stop. Yes.
Yeah.
But it will be transparent to you.
No, it will stop anyway. You're just talking in terms because you kind of got used to run the model on a particular machine. I mean, on this discover.
Oh, that's true. The
Yeah,
automatic
But
restart. Yeah.
automatic restarts, not
Okay.
everybody is using it even
Good
there,
point.
so
It's the nature of our queuing system. Jobs can't run for
Yeah.
more than 24 hours. So when they
So-
resubmit, they reread the I file that you've modified, and then they go in the queue with the changes.
Okay.
Yeah, but.
Yeah, so if you're running it in one go, the whole thing, then yes, you will have to stop and restart. Yeah.
Okay, any other questions? Anything in the chat? Are we
No, the chat is good.
good?
We'll take care of it.
All right, then we move on, and our dear colleague Igor Alienov will take over. I can advance the slides.
Yeah, I guess. So, yes, I will be talking about ground hydrology, and if we have time, we may look a little at Mars on deck as an example of basically land surface planet, nothing else. So ground hydrology, basically you need something on the ground to, as a boundary condition to run your model. You have to have all the fluxes at the bottom and you have to have albedo of the surface. So different models have different each model has some sort of land surface every GCM, but complexity is different. So our probably is some kind of middle complexity, I would think. So what we have ground, we have soil, we have vegetation on top of it, and we have snow on top of soil, and also we have lakes and rivers that connect that lakes. So it's a lot of stuff. So basically, speaking of ground hydrology, we have 6 soil layers which go to 3.5 meters deep. Then on top of it, we can have 3 snow layer snow model, which basically can get as thick as you want, but we already discussed some parameters which can be used to restrict the thickness of snow. So if the model accumulates too much snow, it will be removed and basically dumped into the ocean, kind of simulating of moving of land ice over ground to the oceans and creating icebergs, but that's a hackish approach. Then we have vegetation, which is kind of complicated. We call this ant vegetation model. I guess there are some applications on it that we can put for those here. So yeah, and vegetation, basically the main the goal of vegetation is simulate transpiration. That's movement of water by roots to the leaves where it can evaporate. And inside the ground, you have infiltration of water from top to bottom by gravity and capillary uptake by capillary forces, and we have surface and underground runoff, which basically takes water to underground streams and that takes it to the local lakes and this is discharged to the rivers. So the plot that you see here is kind of complicated. That was created, the whole slide was created by Nancy Young. She likes complicated plots. Nancy Young is the person who doing most of the vegetation modeling for our group. So on the plot we see here, basically the bottom is soil, then there are trees, and there are 2 sections on the left. We see vegetated part of the soil. On the right, you see bar soil. So those are 2 fractions that's modeled separately in each cell. And these arrows show a lot of fluxes. Actually, these are just heat fluxes. We don't even show water fluxes here. So as you see, things are quite complicated. I don't think I have time to describe all of those. So, but basically, yes, mostly on vegetated part, mostly it's canopy which interacts with atmosphere. It gets all the fluxes and then basically fluxes passed by the canopy to the ground. We have the functionality to enable some fluxes through the canopy, but I think they're disabled by default in most of the run decks on Planet 2 branch. But I guess you can look at the examples of our run decks. But basically, I probably shouldn't go into more details. This, yeah, So in terms of lakes, we don't allow lakes, you can have a lake which occupies 100% of the cell, but if you enable dynamic lake, which will automatically change its area depending on its size and basically on the profile of the lake bottom, then we don't allow lakes to expand to more than 95%. Just for technical reasons. Yeah, and lakes can operate completely if you like, so. Probably can switch to the next slide. So this basically just repeats the same thing, except now we list, at the bottom of this slide, we list all, probably not all, but the most important input files related to ground hydrology. So veg file describes your vegetation distribution. We can have to 16 vegetation types, and also we can have 2 types of barbarous soil, basically bright soil and dark soil, and that defines the albedo of your soils. It's mixture of bright and dark soil. Top index, well, it's a funny name, but actually you just have to specify a standard deviation of topography in this file. Soil just describes soil texture. We'll look at this some of those files in the moment. Rough is specifies roughness length, and soil IC is initial conditions for soil ground hydrology. Some next slide is yeah. Well, and now I'll just go over Mars as an example of ground hydrology. So next slide. So this here we're looking at the soil input file. This is just header. As you can see, this nc dump command. So basically it shows you what one has here. At the top, of course, those are just dimensions of this file, latitude, longitude, distribution, then 6 layers of soil and 5 types of vegetation. Oh, no, sorry, 5 types of soil type. So, and at the bottom, you specify D is thickness, Q is soil thickness, QK right now it's the same file, same information basically repeated, and SL is a local slope. Slide is, so this is soil IC file. That file you will really probably modify often if you run ground hydrology, I mean a land surface model, and I'm interested like different input conditions. So it's very simple. You basically just have to specify wetness of soil layers from 0 to 1, 0 being completely dry, 1 is completely saturated. You can modify snow thickness in terms of water equivalent, and you specify soil temperature for actually. Next slide is and this is vegetation file. This is again for Mars, so it may sound like silly vegetation for Mars, but this file also specifies soil colors. So we have now in this file 2 types of soil, dark soil and bright soil, and the definition is that dark soil has 0 albedo and bright soil has 0.5 albedo. So in theory, you cannot have soil brighter than 0.5, but actually you can apply hack just using negative fractions of soil that we don't recommend it. So basically up to 0.5 albedo. So yeah, I guess next slide. Yeah, so this slide just shows you how soil albedo is specified for Mars. So upper 2 slides are just fractions of bright soil and dark soil. On the left, that's bright soil, and on the right is dark soil. And if you mix them together, then you get albedo, which is shown at the bottom of the slide. except that it's a real albedo, so it includes not only soil albedo, but also snow, which was basically deposited during the run. So at the North Pole, you see it's basically northern winter, so you see very bright albedo because of CO2 snow that was deposited in this Mars run. Next slide. Yes. Now we are just going to. Basically, this is kind of like repeats what you have should have in Mars run deck, and that kind of repeats what Mike was talking about. So this is basically specify that your planet is Mars at the top of your run deck, and then you specify eccentricity, obliquity, longitude of periapsis, sidereal, orbital period, rotation rate, and yes, we said quantize here too. And for Mars, we use, at least in this one deck, mean distance instead of planet as zero. So one basically you should use only one, either planet as zero or mean distance. For Mars, it's convenient to use mean distance because we know it, and then we don't have to modify planets as zero. So this next slide. Yeah, this basically just shows it's the same information that is printed in the log file when the model starts. So it's a good place to check that your run deck really was read, and that all the parameters that you set in the run deck basically were understood by the model. So yeah, next slide please. Yeah, and again, this is just continuation of this log. It's interesting to look at the calendar that basically shows you which calendar will be used. So you see that Mars actually has 600, I guess, 69 days. So each month has certainly more than 30 days. It's like close to 60 in general. So you see, but you still have 12 months. You can check it here. It's also out from the log files. I can check it. Sure, if I have anything. Yeah, this just basically shows the most recent simulation for Mars pressure for Viking side. That's as good as we get with Planet 2, though it actually with Planet 2.1 branch, which will be released very soon. With Planet 2 you can get close, but the significant improvement in Planet 2.1 will be new snow model. Here in Planet 2 we still use for CO2 we use basically bucket model, snow model. So it's just the amount of CO2 deposited at the bottom, but it don't have any structure to it. It just defines albedo and basically the amount of CO2 stored at the soil. And in new model, you will have multiple layers of snow, which can be mixture of CO2 and water snow. So that's much more flexible model, and it's currently being tested. But we didn't release it in Planet 2, but we released it, so it's extension Planet 2. So I think I still have 5 minutes. Or,
Yeah.
so I think,
You want to talk more? Or
I can share then. Maybe if I can share.
Yeah. I can stop sharing.
Yes. Screen I can show.
Stop. There you go. So you should be able to share now.
Uh, so basically here I have already created the Randex with make Randeck and you see Microsoft?
Yes.
Yeah. So PS Mars took its PS Mars, I guess. Kosov already talked about it a little. This other Randeck, it's a new Randeck on Planet 2 branch, which is more advanced Mars Randeck. So if we look at the original Randeck, those, by the way, are from Planet 2 branch. So even PS Randeck is slightly different. I don't think we have this. PS Randeck basically is different on Planet 2, only that it includes CO2 condensation, and you enable it by specifying this CPP options at the top of the Randeck. You basically don't need to do anything else to enable it with the new model. I mean, Planet 2 model. Otherwise, this Randeck is basically the same as on Planet 1. So I guess I want. So yes, it's source files, which we also basically. That's what I wanted just to go is input files, which are probably most interesting. So just to show you how simple this Randeck is. So you specify AIC file, which basically is just atmospheric boundary conditions. Then soil IC, which I just showed you these conditions of the soil. Specify you specify topography, and you saw the topography visualized before. Top index is just standard deviation of this topography. You specify a roughness length, it's a roughness length, and we currently use just the same value all over the Mars, just typical desert value, so that can be improved and didn't have time. Soil, for soil we use all sand here. And, for which also I showed you this file. This is greenhouse gases, already was talking about, and a couple of radiation files that you should touch, and basically that's it. So I think else here, so everything else is trivial. And just one thing I wanted to show you. The difference between this simple Randeck and the new Randeck, which we provide on Planet 2. So basically what it does, it includes also a dust cycle. So on the right is old Randeck, on the left is new approved Randeck. So you have to specify certain options, CPP options to enable tracers and dust. Then in source files, you have to specify model source files. You specify extra files needed for tracers. Then you specify new input files. Yeah, for basically for dust sources. And then I guess Eric will be talking about spectral files. Those files are needed for Socrates. So when you run the model with dust, you need extra files which deal with aerosols, because basically dust is an aerosol. So that's what was improved. And then there were a few changes just for stability reasons. And this is a big section for setting dust parameters. That's basically how you want to run your dust model, and pretty much that's it. It's just a few timing changes just for stability reasons. And so that's basically how Mars Randeck has improved, and that's the difference between trivial desert model and the real Mars Randeck now. So since I'm out of time, I guess I'll stop here.
Okay, any other questions? We've had a few in the chat. Okay, cool. And maybe you could stop sharing.
Stop share.
Should
Give
be-
us
There-
some,
there
yes.
is like-
Any other questions about the things we discussed? Yeah.
We just trying to understand the rivers versus lakes. Do you've mentioned that now you don't have to specify river direction. Do you need to like specify that there are rivers connecting different grid cells if you want?
Yeah, I guess I would be less optimistic than Mike is, and if you know river directions, I think, it's probably good to specify them, or it depends on what you're trying to do. Usually for Earth, for example, when you know topography, you will get probably more accurate results when you specify rivers, but it just makes your life easier if you specify rivers by looking at the topography anyway, then now model will do it the same thing for you automatically. So basically the model just looks where the level of water is higher, where it's lower, and your river will be going in that direction, and that sort of changes dynamically. So if you like seasonally accumulate more water in one cell and then in another cell, then basically river will flow. And this level basically includes also topography. So if you have like certain topography and certain amount of water accumulated each lakes, and it will basically water will always go downstream unless topography is very flat and you accumulated too much water in some cell, then it may go even against topography if you accumulate a lot of water. But the river is always, I mean, you don't have like a real river, it's just basically the amount of water you move between cells based on difference between the height of the lakes and yeah, I think that's just the height of the lakes.
And think of it that the model does not have rivers, although you spoke about rivers, it has lakes, and the rivers are are the fluxes, the implied rivers are the fluxes from one lake to another.
Okay, so you don't have to define like there's some kind of river connecting these two grid cells. It's just based
Not
on.
necessarily.
Yeah, on planet 2 you don't have to because it will be done automatically. But on planet 1, yes, there was a file where you actually were specifying, oh, from this cell, river can go only to this cell. So basically it was just one direction, just once, or always only one downstream cell. You can still do it in planet 2.
In fact, the lakes and river algorithms were completely rewritten for Planet 2.0. That's described in detail in the paper that Kostas Sigarides is leading and should come out. Well, we should be posting it in the coming weeks. So you can see the details exactly the changes we made between Planet 1 and Planet 2 because they are significant.
Yeah,
And the group that did the changes claim it's greatly improved.
Is there any routing scheme for movement of water on?
The scheme's
Yeah.
built into this Planet 2.0. They've rewritten the scheme for doing that.
so you can,
In
you
Planet
can still
1.0, there was
define,
no scheme.
you can still define rivers if you want.
Yeah.
So if you are on Earth and you know where the rivers are, you can still define them. But if you don't know, or if you are creating new topography for whatever reason, then you can let the model decide by itself.
In Planet 2.0. In Planet
yeah.
1.0, you have to define where the rivers go. In Planet 2.0, it can do it for you based on the topography.
It's all based on topography. So if you have cells like this and the lake overtops this one, it knows that it's gonna flow.
So it's gonna be fully conceptual. There is no somehow governing equations for that, how water routes from one space to another. We have shallow water equations that we can use, we normally use for river routings.
Well, this we compute the speed of the flow, but I don't remember exactly what's the equation. But basically, it's kind of proportional, I guess, the difference of heights. So the steeper basically is the slope between the lakes in two cells. The higher will be the speed, and we also have seal depth. So it's kind of like. A river starts to flow only when you are above this seal depth. So I guess the amount of water you move also depends on the height above the seal depth. That's basically kind of like the height of water in your actual river. So basically, yes, it's kind of proportional to both the amount, the speed of the river. Then the flux is proportional to the amount of water and to the slope.
And like Kostas was saying, that an actual river is good cell size. So you're really just moving water from one cell to the other. Correct.
What about big rivers, for example?
There are no big rivers.
Yeah,
The-
they're bigger
the
than
Amazon is
4x5.
The Amazon is a collection of lakes.
Yeah.
Yeah, basically the water surface itself is assumed that it's lake. So if a river big, then yes, you assume that it's kind of lake, which basically stays in one cell, but also exchanges the lake, the water with the lake and then to another
It's
cell.
for the sake of resolution. The
Yeah,
resolution is so
resolution.
much close that you
Yeah.
cannot. have
And also when a river, in terms of surface area, is a fraction of a grid cell. Whether you create that fraction of a grid cell being a line or a circle, it makes no difference for the model itself.
That makes sense.
Yeah, and also one thing I didn't mention that we assume that all our lakes have conical shape. And it's kind of like approximation, but you have to start from something. So the slope of those basically of size of the cone can be different depending on your boundary conditions which you prescribed originally, but still seem to be conical, and that's how you compute the area. The fraction basically of the cell that is occupied by lake, depending on the amount of water that is created there.
Okay, let's take a break here. We'll start up again in about 12 minutes or so. Pause this. Hello, everybody. We're back. Forgot to turn on the audio. We're going to cover I'm just going to cover 2 slides very quickly before, or maybe 3 slides before Eric takes over and tells us about rate of transfer. A couple things that I thought were important to discuss.
Does that mean we have to go?
I don't know. We just had a notice in the building about some kind of
Go check.
thing that we may have to do. So just a moment.
Can we just lock the door?
We just locked the door, Igor says. So they said there's some kind of emergency action plan that we may have to participate in. So just hold on for a moment. I'm going to pause the recording here. Okay, we're back and we have not been kicked out of our room. So as I said, I wanted to cover a couple things before Eric takes over here related to whether you can tell the model is in equilibrium or not. There are a couple different kinds of equilibrium in the model. One is radiative equilibrium and one is hydrological equilibrium. I think we said yesterday, in general, we would like the radiative equilibrium, which is basically the difference between the ingoing and outgoing radiation at the top of the atmosphere. That value should be somewhere between plus or minus 0.2 watts per meter squared, if at all possible. And that's what you can see plotted here in the top graph, basically. These are a bunch of model runs that Kostas has run as part of the Planet 2.0 paper. They're not all in equilibrium, as you can see here. If you look at, for example, the blue run, it is looking like it's pretty close to equilibrium, as well as the purple run, but you can see the red run has not quite gotten to equilibrium yet. And this particular plot is generated from the NetCDF files that come out of the model. This is called net rad planet. So this is actually net rad planet underscore hemis, which is the global value of the radiation at the top of the atmosphere, the balance at the top of the atmosphere. You can see that some runs come into equilibrium faster than others. So the purple run is coming to equilibrium in about 250 years where the blue run took about 500 years. And then we have some runs in light blue and green, which are not quite in equilibrium yet. That means we need to run these runs a bit longer. So this is one of the things that you should plot, one of these time series plots as you're doing your runs, to make sure the planet is in equilibrium. You don't want to publish a climatology for a planet that's not in equilibrium, because as you can see in the bottom panel, its surface temperature is changing through time and may not be the right surface temperature because the model's not in equilibrium. So if you look at, again, this green line, you can see that it's still changing as we're moving forward in time, although it's starting to level off a bit. Whereas the blue line has some variation through time, but it's more or less becoming stable by around 500 years. Whereas, for example, the yellow and the red lines are still moving quite a bit, so they're not in equilibrium yet. So these are things, important considerations to consider when you're running the model forward in time. Here is another example of a time series plot for a particular run, where in the top panel, I'm showing this net red planet, as we saw in the last plot, the surface temperature. We've also plotted the global planetary albedo. The fourth panel is a cloud diagnostic, ocean ice fraction, and sea ice depth. And you can see everything here is very stable and acting very nicely. So that's a good sign. And you can see that our net red planet is about 0.13 watts, which is good. Here's another example from a run of ours where you can see, for example, ocean ice fraction is fairly flat. A G ice is the amount of ice in the ground. ZSI is the thickness of ocean and lake ice. That diagnostic in particular, you can see, is still moving upward. That's not a good sign. That means this model's not in hydrological equilibrium yet. So these are the kind of diagnostics you want to look at depending on the kind of run you have. If you have a land planet and you don't have any ground hydrology, for example, then some of these diagnostics will be zeroed out. It won't mean anything. But if you have a planet with large hydrological sources, like big ocean or a lot of lakes, these are things that you want to consider plotting through time to see if your planet is in equilibrium or not. In general, these hydrological cycle diagnostics take longer to come into equilibrium than the radiative balance at the top of the atmosphere. In general, that is true. Okay, so at this point, I'm going to let Eric take over and tell you all about the radiative transfer in the model.
Okay, great, Mike. I assume you just want to keep the screen up, and I can just cue you for next slides rather than do a screen switch.
Yeah, that'd be great.
Cool. All right. So, hi everybody. For those of you who don't know me, I'm Eric Wolf. So I'm at the University of Colorado Boulder. I've been sort of the steward of the Socrates radiative transfer model within ROCKE-3D for the last number of years. So as you can see on the screen, Socrates is a long backronym for Suite of Community Radiative Transfer Codes based on Edwards and Slingo, who were two scientists back in the, I believe, 1980s at this point. And so Socrates has its origin at the UK Met Office. It is in the UM United model or unified model, and also used in the UK Met Office weather modeling. And it's also been ported to ROCKE-3D by David Amundsen, who was a NPP at GISS many years ago. And it's also been started to be ported to some other models too. I believe it's in the ISCA code, which is another European model. So next slide, please. So what is radiative transfer? So radiative transfer is the transfer of electromagnetic energy through a medium, and then this medium being the atmosphere. So the sun's energy, as you can see on the left of this, kind of very common energy budget type plot that you can find, the sun's energy permeates downward through the atmosphere, reflected by clouds, reflected by Rayleigh scattering, absorbed by gases, hitting the surface, absorbed at the surface, reflected back by the, back upwards from the surface. And then there's the other part of the radiation budget, the long wave, the thermal emission is emitted by the planet, the black body radiation of the Earth, and permeates upward through the atmosphere to space. It's absorbed by greenhouse gases and clouds. And while we commonly parse the long wave and the short wave streams of the radiation, we do this out of convenience, out of kind of mathematical convenience, if you will. The electromagnetic spectrum is a continuous thing from long wave to short wave. For Earth, it's very easy to split long wave and short wave streams right around 5 microns. And actually, for exoplanets, when you start modeling things like TRAPPIST-1e, that the spectra from the star is so shifted into the red, if you will, that there is a kind of an overlap between what the star is emitting and the planet's receiving, and then also with the greenhouse emission or the long wave emission from the planetary atmosphere. So this balance, as the last sentence here, this balance can be very different for other planets compared to Earth. This graph shows Earth's energy budget with respect to radiation, but it can vary dramatically when you start changing the star, changing the atmospheric composition, those two in particular. So next slide, please. So we can take a look again. This is focusing on Earth's radiation budgets. You can see on the right-hand side the kind of what I was describing previously. You have the red portion there is the downwelling solar radiation from the sun, and then you have the upwelling thermal radiation from the Earth, and they're kind of divided into two separate regions based on the black body emitting temperature of the Earth and then the emitting temperature of the sun, which is about 5,600 Kelvin. And then below, you can see the total scattering, absorption, and the different components from Earth's atmosphere, where the major components are water vapor, carbon dioxide, oxygen, ozone, methane, nitrous oxide, and also Rayleigh scattering. But different planets can have very different mixes of gases. And even if we think of just the early Earth, which had carbon dioxide values that could have been, 10, 100 times greater than now, and same with methane. The early Earth also didn't have any oxygen or ozone in the Precambrian, and also there was the chance for forming photochemical hazes, which aren't included on this major components graph, but could have existed on the early Earth. They exist on Titan. So for radiative transfer, it is one of the more expensive parts of the code. So they're often very tailored to specific compositions. So Earth-based, the vast majority of climate models started as Earth-based models, much like the Model E for NASA GISS. And then we've migrated them over to be able to be more flexible to handle exotic atmospheres for paleoclimate Earth and also other planets and exoplanets. But this is most often required the incorporation of new and more complicated and more expensive radiative transfer codes. And so that's where Socrates fits in. So Socrates is not used in the core Model E for NASA GISS. They have a tailored tightly to Earth radiative transfer model, where Socrates provides us a great deal of flexibility in order to change the specifications of what gases and aerosols we are considering as the absorbing species in the model. So next slide, please. So Socrates, as I've said, it's a radiative transfer model designed for use in 3D climate models. And that's an important distinction, because the best radiative transfer models, so-called line-by-line models, are way too slow and way too computationally expensive to run with a 3D climate model, where if you are using your nominal 4x5 degree resolution grid, that's over 3,000 different grid boxes, and you're doing a radiative calculation in every one of those grid boxes. We don't do it every time step. We do it every few time steps. That's a tunable property. And I think in ROCKE-3D, every 5 time steps is a common one, but probably no more than that. So there's this balance of trying to get this fast, flexible, fast, and accurate radiative transfer model while also simplifying the problem down from you can't do a line by line calculation. You have to do larger spectral bands, so you can limit the number of bands to tens of bands over the spectrum instead of, in a line by line calculation, they're doing one calculation every 0.1 inverse centimeters across in wave number space. So Socrates is very good at allowing us to make these flexible so-called spectral files, which we can tailor for different sets of gases and aerosols. And there's a separate spectral file you'll see in the run deck for each of the long wave and short wave streams. So those are kind of easily separate in your mind. The short wave stream is the sun's energy. The long wave stream is the planet's energy, and how those filter through the medium, which is the atmosphere. Another thing that's incorporated, of course, is the incident stellar spectra, and this is a nuance of Socrates, is that when you're using or making spectral files, the incident stellar spectra is convolved into the shortwave spectral file in order to improve accuracy by doing a weighting within each band and across the bands to do a reweighting to the actual incident stellar spectra. And then also you will be specifying the total amount of stellar energy reaching the planet, which is the fixed number, 1360 for Earth, 900 watts per meter squared for TRAPPIST-1e, things like that. So next slide, please. Okay, so this is the list of the important documents. So Mike, if you don't mind clicking on that first one, the user's guide. And we're not going to read through the whole thing, but this is a great resource into just getting some of the, and yeah, you can kind of slowly scroll down, Mike, that's fine. Just some of the basics, how to set up paths, what part of the run decks are relevant. Yeah, you can keep scrolling down. As you can see, setting in the run deck there, spectral file LW, spectral file SW. Let's see, the solar spec is specify what your solar spectrum is. There's aerosol optical property files, which aren't, there's more not commonly used, but they're there if you need them. And keep going down. Thanks, Mike. Let's see, and then let's see. I don't want to get too much into the weeds, so let's see. Keep scrolling down. I mean, this is technical details, checking for accuracy of spectral file. It's spectral files. It's things that David and I have done previously. And then you can keep going down, Mike. I think the next one, changing the stellar spectrum. So this is if you want to make new stellar spectrum, there are instructions how to do that here, because you don't just have to make the new stellar spectrum. You also have to run a script that convolves it with the shortwave spectral file. You can keep scrolling down, Mike. Thank you. Let's see. So yeah, I mean, this is sort of into the weeds as far as changing the stellar spectrum. I'll leave it to you all to read through this document at your leisure. If Mike, you wouldn't mind switching back and going to the next one, which is the list of spectral files, which I think is the more important one I wanted to talk about today. So in this document, we have the list of stellar spectral files or spectral files period, and the stellar spectrum, along with some of the details. So if you scroll down a little bit, Mike, I have this word on select. Yeah, that's good. We'll start here. Above there is a little thing. I have this word on selecting how to select these, which is, sort of common sense, which is choose the spectral file which most closely matches the description and the mixing ratios that you're using for your particular simulation. So first we have several basic categories. The first here being present day Earth, and then there's this, there's a regular present day Earth, and there's a more robust present day Earth, and then we have a Proterozoic Earth, and then Archean Earth, which are no oxygen, as I should say, the Proterozoic is a little bit of oxygen. The Archean is no oxygen, but high CO2 and high methane. And there's numerous different permutations of the Archean, from kind of lower methane and 1 bar atmospheres up to very high methane and 10 bar atmospheres, and then different flavors, adding nitrogen species and Blazarchean, named after our collaborator, Vladimir Erpatian. And then we can keep scrolling down to the next one, which is, let's see, these are still more permutations on Archean, this broad brush of the Archean. And then we have Mars through time, which is really defined as CO2 dominated. So Mars, currently is pure CO2, just about, but only a 6 millibar atmosphere. We think early Mars may have had a denser CO2 atmosphere, multi-bar atmosphere. So we kind of throw all these high CO2 dominated cases under this Mars through time. We have modern Mars and then Paleo Mars, which adds in methane and hydrogen. And then, there's a lot of technical details here about specifics, which, you can, feel free to email me about. And then I think after those are the kind of the main few, is Earth through time and then Mars. And then there's a few other worlds which aren't commonly used. Titan, which I'm not sure if, Mike, you can correct me if a Titan version has been spun up in 3D. And then early Moon, which is a very thin atmosphere that Igor has been working on. And then lastly, we'll get down to the stellar spectrum. We have a large variety of stars that we've used over time here. You can see the sun at different ages. The sun is a red giant, and then a whole list of different real stars, and then also some model theoretical stars, ranging from very cool like TRAPPIST to 2600K all the way up to G stars. We haven't quite broached the F stars. That problem hasn't. If that's becomes something of desire, there are a little extra work needs to be done, because the F star spectrum and hotter start to push the energy actually shortward of the grids that were currently used. So one would have to add some extra shortwave grids, shortward of about 3.3 microns. Yeah, I see some of the comments. Yeah, one of the reasons why we haven't really done much with F stars is that the lifetime of the stars is inversely proportional to the mass. So as we're thinking about looking for biosignatures and stable life somewhere, these hotter stars are progressively shorter lived. But yeah, if Vincent, if you want to do a F star project, talk to me. We have to change the gridding a little bit with Socrates, but it's not that big of a step. It just needs some motivation. So yeah, I think that's a very quick and dirty rundown of quite a complicated topic. The last two we don't need to click on. These are advanced user stuff, the technical manual of equations and what's going on, and then the user's guide. So a last point I will say about Socrates is sort of a kind of my 2 cents of the philosophy of how Socrates is working, that it operates with a lot of pre-processing scripts to create these different spectral files, and the code is very flexible, but so that it's great that you can use and manipulate it without actually having to do any hard coding. But it also, that introduces its own complications, because sometimes the scripts can be complicated in and of their own right. And then looking through the code, they use a lot of dynamically allocated arrays, which allow it to be very flexible, inputting different spectral files without having to change the hard code. So it's a great model. It's a great code. It has its own particular challenges in use, just like every code. So yeah, I'll leave it at that. And I unfortunately have to run out and do a previously scheduled errand, but I am going to log back on at noon New York time in order to be here for the Q&A. So if you have any questions, save them for then.
But the Q&A is at 2, Eric, not noon.
Oh, I'm sorry, noon my time, yes.
Noon your time, yes.
Yes, noon my time, yes.
Okay, thank you, Eric. Thank you so much.
Yep, cool. All right, I'll see you guys then.
Great, so thanks to Eric, and now we're gonna move on to the planetary spectrum generator, which is developed out of Goddard Space Flight Center. And Vincent Kaufman is gonna talk to us about how to use that with 3D inputs from GCMs like ROCKE-3D. Are you there, Vincent?
Right, I'm here. Yeah, good morning all. I hope you can hear me well.
Hear you great.
Thanks. Yeah, thanks, Eric. I know you just dropped off, but thanks for the introduction on radio transfer. That'll be very helpful for this tool, obviously. So yeah, I was asked to give this talk. There's a lot of work that I've been doing together with Geronimo and with Thomas Fauché and other people of the PSG team. I gave a similar version to the ExoVast seminar series that's run out of Goddard here, but I've really added a lot of detail here specifically for Rocky. So and as I understand it, Mike, the slides will be available online as well. So I put some resources in there. Hopefully that'll be helpful. Yeah, and if you can proceed to the next slide, I have a short introduction about the planetary spectrum generator, and I don't know why the text is not showing up because it's in white here on.
Oh, there we go. I have to scroll through it. Sorry.
My bad. Okay, no worries. Yeah, so just as an introduction in general, PSG is a radiative transfer tool. So what that means is you can simulate what spectra would look like from different objects, using different telescopes or different orbiters. It directly links to the exoplanet archive, so you can put in your exoplanet and figure out what the specifics are of this system. It is case sensitive, so you gotta sometimes be a little checky there, a little careful. It's got solar system objects. There's a noise simulator with where you can essentially have a whole bunch of different templates that you can consider. We won't go into that here because it's kind of a different beast. But if you have any questions about that, there's literature available, and it'll be described on the website and in the handbook as well, which we'll see. We now recently have installed a grid-based retrieval system as well, so you can do grid-based retrievals or just normal the old school way. And then what we're mostly going to be focused on here is the globes module for ingesting global circulation models. There's a couple of examples out there of papers that have done this, but the bulk of the description will be coming out soon, and I have the titles of the papers coming up. So, Mike, if you proceed to the next slide, please. Yeah, so here's we see the famous interface. We have here we have a template exoplanet. You can see there's a short description here at the top where we see the name of the exoplanet, which is in this case so exoplanet. Then essentially the tool is sort of divided up into 3 different buttons. You can change the object, which is where the geometry of the object describes the size of the object, etc. Then the composition, where we can go specifically about the atmosphere and the surface and change some of those things. And then the instrument is where you can sort of define the sensitivity of what wavelength range you're interested in, and where you can look at the instrument settings like that, really go into the noise modeling and all that. But we're not going into detail too much there, as I mentioned. Then there is we've been trying to be diligent about providing documentation. So we wrote a handbook. This was all funded by SEEK. So we put in a SEEK proposal, and SEEK paid us essentially to get this handbook printed. So we have a couple of paper versions out, but the PDF is being updated almost weekly by Geronimo. So if I would always recommend go to the page and download it there. The link will be on the following slides. There's also some tutorial videos. They're about 10 minutes each. They go over the different chapters of the book. Essentially, they've been recorded about 2 years ago, but it's a good introduction and gives you an idea about like what the different sections of PSG mean and what you can do there. Then if you proceed to the next slide, Mike, then I think this is where the links are. I guess they're popping up as we speak. Yeah, so we have the code repository. That's where the sort of a whole bunch of scripts are that translate netcdf files from different GCM files into the PSG binary format, and we'll go into a lot more detail there later. The main website, and then there's the different materials for the tutorials, the handbook, and the parameter list. So the first link is essentially a slightly different version of this seminar that was recorded here at Goddard. Yeah, we can keep going there. Pull up the overview of slides here on the side. yeah, so these are the two papers that we're now working on. The first one is under review, and it'll describe a lot of details of what I'll be showing in this figure or in this talk. And then Thomas Faché and Geronimo are leading another effort where we're really describing the globes module in a little bit more detail. And then my paper, the pale blue dot, is more of more of an application, but due to the nature, there's a lot of descriptions too on how to proceed with all this and like ingest the files and all that. So that's partly what we'll be talking about in this talk. And on the next slide, I have a short outline. What I was thinking for this talk is I'll first go over the principles of PSG and globes, because I think it's important. Obviously, just like ROCKE-3D has a strategy of getting to results, PSG also has obviously a bunch of different steps that you should take to get to your simulations. And the easiest way to do this is really to just sort of start from templates that we have available, and then sort of modify those as you see fit. Then I want to show a couple of use cases, because I think that they are instructive on, first of all, obviously what you can do, but it also like is a step-by-step on how we get to these kind of results, right? And then if we have time, we can go over a quick demonstration. Then on the next slide, I have we have there's a little bit of a detailed slide, but essentially it goes over our modeling atmospheric absorption and the way the different things are incorporated. So for the planetary spectrum generator, right, that we talk about the geometry, which is sort of the first topic here, right? So you have the ephemeris and you have the flux calculations. What is the size of the star? What's the temperature of the star? What stellar spectrum are you assuming for the star? All these kind of things you can change in the geometry section. And then what this code essentially does, right, is it makes a photon budget as a function of wavelength. And that's where all the other steps come in. So you have a radiative transfer code, which incorporates the atmosphere. There's a whole bunch of atmospheric databases that are being used. So we use the Hydron database. We recently incorporated ExoMol for the more exotic species and the more relevant species for hotter atmospheres. There's high temp as well. We have a parameter or CIA parameterized version of the water absorption continuum, if that is familiar to all of you. That's particularly for long wave radiation, the water, what they used to call water continuum, or what we describe as a collision-induced absorption, makes a big difference in terms of the radiative balance of the Earth's atmosphere. And we parameterize that so that it's easier to use, and we can actually use it for exoplanet atmospheres as well. Then I mentioned we can do retrievals as well. I won't go over that in this talk. And then there's the instrument detector and noise model. So these are essentially the three different boxes as we see them in PSG, and here they are sort of described in a little bit more generally used scientific terms, right? Then let's go to the operation principles on the next slides. I have them here as a little figure, right? So what I always do is I start with the template configuration file. So that is, if you're on the home page of PSG, you can click through basically the first box that you see, and we'll do a quick demonstration later. But it's the select template box, and there's a whole bunch of templates there. So it's ranged from comets to Mars to exoplanets to Titan. And I would always make sure you select something in the right wavelength range that you're interested in. I've had people working with Venus and taking a Venus template from ALMA, which obviously is in the radio. So a lot of not the full atmosphere is being selected for radiative transfer purposes. That's in that case. So always be sure to check what your inputs are and what you're calculating. So that's the configuration file. Then what we need to do to run essentially the globes module, which is the module that interfaces with PSG, interface between netCDF files and PSG, is a specific binary format. And this thing is a little tricky, so it'll take you a little bit to like get the details right. But it's a binary file because it's easier to read in for PSG instead of like having a heavy netCDF package where, you know, every GCM and even every run of a GCM might have different information content, and sort of to limit data traffic, we really selected to have a binary file which really only has the relevant parameters that you're studying for the simulation. And then I would always recommend, like, once you have the binary file converted, go to globes and test the file and see that it's written, or PSG interprets it as in the way that you intend to have, because I've had some examples where the ocean temperature varies between 0 and 1 Kelvin, which is obviously a fraction, not a temperature. I've seen some very cool, almost lollipop-like structures where we have winds of thousands of kilometers per second speeding out of the Earth at from north to south. So those are all misinterpretations of the binary format. And I really want to stress this part where, you know, the point of the binary format is, and we have that on the next slide. Or the slide after actually. So if you go to the next slide, we'll go a little bit over the configuration file. But I just want to stress for the binary file, the interpretation or the key that you give PSG is really essential. So the configuration file here, there's 6 different types of parameters in there. That's the atmosphere parameters, generator, geometry, surface, object, and retrieval. Like they're more, I would say they're classes of parameters. So as you can see here, I add a little screenshots of a configuration file that I've been using, and you see here that for each of the sort of the chapters or the classes, there's a whole bunch of specific parameters. So we're looking here at object, it's a planet, object name, it's Earth, the diameter of the Earth in kilometers, the gravity of the Earth, etc. So I've got last I counted, there's about 150 parameters in PSG that you input. The full list is available on the website, and I provided a link at the start there. But I think it's relevant to keep in mind that there's these 6 different parameters. There's also, if we're talking about the configuration file, I think there's one very important distinction that we need to make. And that is that there's 2 ways of operating PSG, right? So you can use the API calls. So that's you send the configuration file to the server, it does your calculations, and you get your results back. And then it doesn't do any checks on the configuration file. But if you're doing this in the graphical user interface in the GUI on the website, what it will do is it will make sure that your configuration file is consistent. So for instance, if you're starting to play around with the object longitude, latitude, and solar longitude, latitude, like those 4 parameters really consistently define how you're looking at the object and what you're seeing from the object, right? But if you then start adding specific seasons or orbital parameters, those conflict with each other. The GUI will make sure that that's cleaned up for you. If you run this as an API call, it will not. So that is important to keep track of, that you're aware that the GUI essentially like checks your homework and makes sure that there's no conflicts there. Then on the next slides, we're going to be talking about the binary file. So as you can see, this is a binary file. I open it here in some hex editor workshop thing. And the reason I show this here is really the file is literally just a stream of numbers, right? So this is how you get your netcdf file into the binary format. You have to supply within the configuration file this specific line atmosphere GCM parameters. And here you see all of the individual numbers. They all essentially define what the size of the binary file format is. So PSG knows what is written at byte number 878575007. That F0 there is that corresponds to a specific number, which might at this point be the temperature in the atmosphere at this layer at that location. And the number, the format of the number is also very specific. So here, as a little example here, and more of this is available on the GitHub page, right? But we're looking here at NumPy arrays that are saved in a certain way. It's important to mention here that they are saved as float 32s, which, you know, if this is something I didn't figure out until I got a whole lot of very weird spectra coming back and a very strange looking planets. But there's all these very specific things that you need to keep in mind, and it's not overly complicated. This is tedious, right? So it's I tried to put all the relevant parameters here on the slides. There's some more details in at the end of the slide. I have a little bit more detail about where these numbers come from. And then in the papers that we're now writing up, they will be explained in a little bit more detail as well. Okay, so on the next slide, I'll show a little bit about the interface of what we're looking at. So this is the globes interface, or part of it anyway. If you upload your file, this is what you'll see. You see the Earth essentially, or in this case, the ground projection of the Earth is default. You can disable that too, but you get the continents essentially lined out with the white lines. then what we're looking at here is the sea surface content. So it's 1 is sea surface, obviously, or is full ocean, and then 0 is no water. So that's where the continents come out, right? Both of your binary and your configuration file you can upload using that button here. It's a little small, but it says upload a config or upload, select the source. You upload them one by one, and as you'll see, if you start upload your config, the GCM file or the binary file essentially will be misinterpreted, so you'll get some funky things going on. But then as soon as you upload the correct binary file, PSG should interpret this correctly. And then what I highlight here on step 2 is check your input. So I would say look through all of the parameters that you're trying to upload and make sure that the numbers that are in there are correct. At the bottom here, you see the scale, and it'll tell you what the range of numbers is. Then once you're convinced that you and PSG agree on what's in the file, you can verify your calculation parameters. We'll be a little further down the page. Make sure that you're selecting the right amount of spatial binning. So spatial binning, I would always start with spatial binning of 200. So then the whole planet essentially gets averaged, and you get one single spectrum back. But obviously, once you have that under control, you should really start playing with that and bringing that down, because you'll see that there's a strong spatial variation within the calculations. And here, I think it's really relevant to point out that not only does this allow you to essentially upload a 3D file and check for different orientations, but there's some pretty strong non-linear effects in radiative transfer, particularly if you're looking at like very high incidence angles, where essentially the 1D approximation works really well for a homogeneous atmosphere or homogeneous surface. But once you start sort of playing around with different types in the atmosphere, so like clouds or other aerosols, or you have ocean with reflectivities, you really just start considering the 3D effects, and this is where globes really plays a strong role. So once you're happy with this, you hit run. So it says generate 3D spectra. Then the results you will see on the left here, you get the spectrum back in blue is the total. And then if you can click on the individual bulbs here, you will see that these correspond to specific spectra, specific locations. So you can just do a sort of a manual check. It's like, okay, well, this planet is supposed to be a quadrature. So what does the west side of the planet look like? Or what does the east side of the planet look like? Does that make sense? And then there's a whole bunch of different buttons here where you can save the configuration file. You can save the layering file, the GCM file. That's the one you uploaded, so you probably don't need that. You can save the hypercube, so that will save the spectra in each of the different locations. And you can save the simple spectrum, which is just essentially the average spectrum at the end of the calculation. All right. If we go to the next slide, as I promised, we'll go into a little bit more detail about different types of spectra you can synthesize. So we can do transits here. In the transit case, you're interested in the extinction of the atmosphere, right? So light goes from the star to the observer, and you're really only interested in how much light's being lost. Layering is important here because of refraction. You're essentially you won't be able to probe the deeper parts of the atmosphere because light's being essentially bent, right? And here the opacity source we consider are molecules, clouds, and hazes. We're not really too interested in the surface. So in Tomas' paper, that's on the next slide. We see some figures or a figure that he's made for this specific case where we're looking at TRAPPIST-1e, which is this is ExoChem. But we're looking here at a GCM. This is from the TIDE project, right? And we're looking at a transit spectrum between 0.6 and 5 micron, and we're looking at the atmospheric depth in parts per million. So essentially, it's the scale of the amount of light being lost with the planet transiting in front of the star. And in this case, you're only looking at light across the terminator, right? So you're really only looking at the light that makes it through the atmosphere, as we saw in the previous image. And here it's important to consider clouds and the size of the bins that you assume, essentially. So it's a little small in the top corner, but you see the full resolution, which is in white, and you see the binning 90 and binning 10. So what does this mean, these binning? The GCMs, of course, they're saved in different bins, And the binning, what we refer here to is we take one bin, and we take the average of 10 bins. So we, instead of doing the full, what is it, like 100 bins across the entire disk and considering them individually, we bin this down by a factor 10. So we're only looking at 10 different spectra there. If we bin it down to 90, I think we're basically down to having only a single pixel. And there you really see that particularly the lower parts of the atmosphere are really underestimating this, because clouds is such a tricky thing where you have the abundance of particles in your clouds, but we don't really know how it's spread out unless we consider this at a higher spatial resolution, right? So yeah, this is where the binning comes in. And then the other type of simulations that you can do are direct imaging, which is on the next slide. So for direct imaging simulation, instead of just lights being essentially being taken up by different sources of opacity, we now need to consider scattered light, right? Because we have reflected light that comes from the sun, it reflects on the surface and goes back out. But there's all kinds of processes that are essentially non-linear, and they're really it's really important to consider light that can be indirectly reflected, so scattered around. So that's what we refer to with the number of streams. So that is, you can read about more about this in the handbook, but essentially it refers to doing the radiative transfer calculation not just linearly, but you're also keeping track of light that's being scattered and then might reach you indirectly. So if you keep going, Mike, there'll be some text on this slide as well. So in this case now we have to budget the intensity, and you can do a little bit more details about surface modeling. And yeah, what I'm trying to say here is like really particular here, the 1D approximation is just insufficient, because the average is not a good description of what you're actually looking at. And on the next slide, I added some details. This is from Geronimo's slides, but there's all kinds of different surface modeling if you're interested. I'm not gonna go too much in detail, but they're out here if you're interested, and the handbook will provide some more detail. Then the slide after this, I'm showing sort of my motivation for doing this study in 3D. So this is essentially one of the paper that I was talking about. It's the pale blue dot, where we're really trying to reproduce images of the Earth using essentially all of the spectral information and all of the weather information that we can find. So we try to reproduce images of the Earth that are such as the one that you can see in the bottom left. So these are from space, looking at the full disk and using high resolution spatial variation to model these. And that's, I mean, we went over some of these details, so we can keep going here, Mike. I like showing that picture because it gives you an impression of the complexity of what we're looking at here, right? And for radiative transfer simulations, particularly in reflective light, you really need to consider scattering by aerosols, and you have all these different arrows essentially that you need to budget, right? So that's it's a complicated process, and it's, I mean, in that sense, it's not too dissimilar from GCMs, right? But now you do it at a much higher spatial resolution, and you need to consider some different effects essentially. So for this work on the next slide, you'll see that we use Earth as a laboratory because it's so highly complicated, right? We're looking at all kinds of like vertical structures, reflectivity of the ocean, all that stuff. We can go a little quicker here. On the next slide, I sort of broke down what we've been studying. So we monthly average ground cover. So it's in the bottom right. You can see the monthly variation there. It's one back, Mike, if you want to pull that one up. Yeah. So here we see the subsolar point, and we see Earth without clouds, and you see the sea ice abundance varying, and you see the snow cover varying. So this is what we ingested into our model, and then separately we added liquid and ice clouds for each of the cells in the GCM, which came from Mera, which is a retroactive simulation tool essentially. So if you can keep going, Mike, here, well, this is GCM bin, we don't have to go over detail. These are the average profiles for the planet. So the point that I wanted to make here, and this was more for an exoplanet audience, right, is the location of the clouds on the Earth really determine how much of the atmosphere is visible, essentially. So we've seen some strong variations where if we're looking at the spectral features of water, they might be covered up by layers of higher placed clouds. So yeah, that's what we can do. And we can go a little faster now, Mike, because even running out of time. So these are some simulations that we've been trying to reproduce. On the left are simulations, on the right are geostationary observatory that specifically looks at Japan and like weather predictions and tornado or tsunami, or what do you call it? Weather warnings, essentially. Then on the next slide, I show some spectra, which you know, that's what they are. We can, like, if you're interested in the science, we can talk about that. Then the one thing I wanted to show is the phase curves. That's just on the next slide. And in this case, I really picked a pretty extreme case where we're looking at TRAPPIST-1b, which is tidally locked. It has a very light atmosphere, and we're looking at reflected and emitted light, and we're doing a 3D simulation essentially. But the reason I picked this one is because on the light side, or the blue side, essentially the left side, the surface temperature is about 150 Kelvin, and on the other side it's about 600 Kelvin. So uploading this into PST, essentially doing all the conversions to the binary format, and then doing a phase curve of this. On the next slide, you'll see what the spectra are at quadrature. So in this case, we're looking at half the planet. It's a tidally locked planet, and you see the backside is much cooler than the front side. So if we do if we consider the 3D model, we get the red line essentially, and if we consider 1D model, we get the blue line, which is like, if you consider the intensity and the differences in the spectral variation, like this is huge, right? Like your 1D model does not capture what's going on here. And on the next slide, I have this as a phase curve simulation. So essentially, you're looking at the different black body temperatures of the object, essentially, right? Because the average black body temperature would be about 300 Kelvin. 300 Kelvin is very different from 500 Kelvin. And since the radiation scales with the temperature to the power 4, the 1D approximation essentially breaks down here, right? So this is something that we've been describing for Thomas' paper. So on the last slide, I have a quick summary here. Yeah, so we demonstrated that PSC can now do 3D simulations using GCM models, including ROCKE. We went a little bit over how to translate the net CDFs into binary format, which, you know, in 5 minutes it's brief, but the basics are there, I guess. And then I want to hammer down, it's like load the configuration file and make sure that you interpret, or PSC interprets what you're putting in correctly. And yeah, keep an eye out for the papers that are coming out here. Thank you. And Mike, you said there was a question hour later on.
There'll be a Q&A at around 2 o'clock is what we plan.
Okay, yeah, I'll dial in for that.
We have 10 minutes now, or we have 7 minutes if people want to ask other questions in the chat, or
sure. Yeah, or I could show the interface. I can quickly share my screen if that's
yeah, we can see. Are there any questions first? And if not, then we can look at the interface. I can just stop sharing here. I think there were some messages, but I haven't been able to keep track of the chat. So
Everything under control.
everything under control.
Perfect. All right.
So you can share your screen if you want, Costa. I mean, Vincent, and tell us
yes.
what.
Yes. Okay. So you should see my full screen now, including my reminders. Yeah. So this is the main interface of the planetary spectrum generator. I would always recommend, before you do anything, if you've been doing anything with PSC, hit the reset button so that essentially your configurations file is cleared and there's no strange setting that might be saved, right? Like it could be that there's some kind of geometry parameter that it is in place that you don't want to see.
Vincent,
the templates. Can
you zoom in, please?
Sorry. Yes.
Can you zoom in, please, a bit? Thank you.
Better. Yeah.
Okay, so here's on the main interface. I was talking about these templates, right? So I like starting with the concept Louvois or Habex. Then if you hit load template, it'll pre-populate everything for you. So here we now have the exoplanet measured via observatory from 10 parsecs. If you hit change object, you get to all these specifics about the exoplanet. And there's a little sketch here of the essentially the orientation that you're looking at. So in this case, we have the size of the object. So the star and the planet in the skies is 0.2 arcsecond. You see there's a white line here which denominates sort of the field of view of the telescope, and you can change that. So if we instead of the fraction limited telescope, we make this let's say we make this a telescope which has a field of view of 0.5 arcseconds. then you get a very different view. Let me see if this works this way. You know how it goes with demonstrations and all that. So that's just the field of view is just the size on the sky essentially. So the size of this white circle is supposed to change. So let's give this one more shot here. Make this 1 million kilometers. And now it's, yeah, you get this tiny little dot here. Great. Then we have the composition here. So this is the atmosphere essentially. Important to point out here is that everything that's in the first box is being simulated by the radiative transfer, and everything that's in this box below is not necessarily considered for radiative transfer. It just has all these profiles preloaded. If you want to change the atmosphere, there's a whole bunch of templates. So if let's say we want to not look at Earth, but we want to look at let's say we want to look for a Venus basic atmosphere, you can load the Venus atmosphere and then it pre-populates that. And then the instrument section is where we talked about, right? So where you can change these specifics. So that's the basics essentially. Then if we, as what I said, right, if this is what we're happy with, we can download the configuration file. We're gonna put that on my desktop for now. And then you'll see here that the file is populated with all the things that we've been talking about. So we have the geometry, we have the object, we have the generator settings, we have the atmosphere settings. We have it's now a Venus atmosphere, right? All that stuff. But now let's go to globes. And as I said, we're going to reset this because we want to make sure that we start with a clean slate, right? Here we have globes. I'm going to make it a tiny bit smaller. This is by default. This is Earth. You see here we're looking here at the winds. We have the albedo of the planet. You can see this in this case, it's just a scale between 0 and 1. And yeah, obviously this changes with location on the sky or on the planet. Now, what I said, I have these two templates I wanted to show you guys. So if I upload my GCM file, which is this DAT file, it's 23 megabytes. It's all binary. And if I open that and I don't tell PSG what is in the file, it'll look like this, right? So now I have a red planet with winds that go 300 or exactly 285 kilometers per second, which this should obviously be the surface temperature, right? So if we now give it the correct essentially GCM parameter decoding list, now we'll see that, oh, look, we're looking actually at the surface of the ocean here. So between 1 here and between essentially 0, you can sort of spin it around, see what else I put in here. So we have snow, and there's some sea ice, which I just call snow because of the, like, keep it simple essentially. We have deserts, we have grasslands, we have forests. And then what I would make sure is, okay, I want to make sure that the water that I'm looking at actually makes sense. So here we have water abundance from minus 4.5 to -1. That's at the surface, but what about all the way at the top? There shouldn't be a lot of water at the top, which essentially the water at the top is between -6 and -5, which, you know, I'm happy enough with that. Then here we have some of the specifics of the calculation. I have a bunch of aerosols here. And this is what we were looking at between 300 and 1,000 nanometers at a spatial binding of 6, which is very low. So I'm gonna quickly change this to 200 so we can generate a spectrum. And now what we're getting is a spectrum of this cloudy planet with the aerosols. And in this case, the units are in spectral radians, which is the measure of the absolute flux essentially. And I'm considering the solar spectrum, so it looks a little bit like probably not what you're used to. So what most people are used to seeing is the IRF. So we can quickly change that. So looks a little bit more familiar. Go to instrument settings. There's a spectral intensity unit here, and let's go to the apparent albedo of the planet and recalculate the spectrum. And then it should look a little bit more familiar because now essentially the solar spectrum is divided, well, should be divided out. But we can disable that one too. So we not integrate spectral stellar templates. Go back to globes, try that one more time. And that's how you essentially get started with these simulations. And it's, of course, it's not doing directly what you expect it to do on an online tutorial. But yeah, you can download the files here. You can go to lower spatial binning. It'll take a little longer to calculate, but then you can start checking whether things are done properly. And then the globes interface limits you to do 200 spectral calculations over the entire disk. But if you install the Docker version, there's some instructions on that on the webpage. You can do up to 6,000 simulations, and then you can really like start doing things even beyond what the typical ROCKE resolution is, right? So no, this is all this is all a lot of material, and thankfully we've been funded by Seek to make some more tutorial material. So what we're planning to do now is really make a bunch of interactive notebooks where you can really like work through the steps of the different aspects of simulating Spectre with PSG and particularly the 3D part. And yes, you can see here's the image that I showed in the slides, and now you can sort of look at, okay, this is apparently at this the west side of the planet we don't get any flux back. On the east side we get a lot more flux back. So in this case we're probably looking at some reflected ocean light that's hitting us directly, which is why the albedo is so high, right? But yeah, I think this will wrap it up, and I guess you guys are about ready for lunch over there. I don't know if there's anything going on in the chat, or there's people working on a different question here. But yeah, please, if there's any questions, always feel free to contact the team. And the material will be made available, or is available to all of you, I guess. So yeah, happy to take any questions. I'll make sure to log on at 2 p.m. then.
Okay, great. Thank you so much, Vincent. That was excellent. Yeah, we'll hold the Q&A for now. If you didn't already put something in the chat, and at 2 o'clock we'll have plenty of time to ask questions about PSG and also about Socrates that Eric covered.
Great. Yep, I'll be there. All right. Thanks.
Okay, great. All right, all. So we take a pause here, and we'll come back in an hour from now. Enjoy your lunch. It's helpful if I turn on the audio for us. So we're back after lunch here on the East Coast. We're going to hand this off to Chris Kalos, who's going to tell us how to build a new planet. Go ahead, Chris. Do you want to run the slides?
No, I'll just share my screen.
Okay, great. Go for it.
All right. Yeah. So we do this this part of the tutorial just to kind of glue everything that we've covered in the last couple of days. I'll share my screen now. So I'll just kind of go through like a run deck, and just it's going to be sort of a more rapid fire version of what everyone has talked about. So, you know, if you grab a template and you're interested in doing a simulation of some new planet, then you know, this will get you started. I'm sure people have seen the news of this planet that was detected a few days ago, this Gliese 12b. It was all in the news. It was all the rage, temperate planet, you know, Earth-like. So so I decided to do this as a test case for this.
Great.
So we'll find out if it's habitable. We can take votes in the chat. All right. So the first thing, so yeah, in your decks, you'll grab a template and then kind of modify. I used so the first thing you need to do, this is a pretty much like an Earth-sized planet. So I just stuck with like the Earth version. But if you need to so we talked about this planet params mod in the model/shared directory, and if you look at the CLC, you know, whenever you have a planet, you know, some new thing you want to do, you have to set certain things in this planet directory, where the gravity of the planet, and the units are described. A lot of them are self-evident, meters per second squared and meters and so forth. You have to set the molecular weight of the air, and this is, you know, Mike mentioned that you could change this, you know, when you're doing a new planet, but it doesn't change during the course of a run. This is one of the reasons why we don't do very hot atmospheres where water vapor starts to increase and become a significant mass of the atmosphere. Partly because the molecular weight doesn't change and the mass doesn't evolve as well. But and then your surface pressure, you know, in millibars. So this would be like a 5-bar atmosphere. And then your kind of mix, your major gases like PN2, O2, argon, and then your greenhouse gases will be set somewhere else, which, you know, we'll talk about. So this atmosphere is going to be, you know, 60% N2 and 40% hydrogen. And sometimes you'll see these numbers don't add to 1 because CO2 is set elsewhere, and that might be, if it's 20% of the atmosphere, then these numbers here won't add up to 1. Anyway, so, and the one we usually use for Earth runs is, if it's not Earth exactly, we have this thing called not Earth, which is, and then there's an anoxic Earth, which is like no oxygen. Not Earth actually is Earth. It's just you need something to be declared here in order to change certain things like the orbit. Otherwise, the model defaults to everything that is actual Earth. So anyway, that's, yeah. So just, you know, put entries for your new favorite planet. I'm going to be using the anoxic Earth for this Gliese run, just because yeah, the radius and gravity were estimated to be around Earth, and you know, it wasn't really worth changing, and we don't know. I just used an Earth, like kind of a nitrogen dominated atmosphere, because we don't know anything about what Gliese atmosphere is. So. And Earth has a pretty gentle atmosphere as far as the greenhouse effect, though. So you know, if you're interested in the inner edge of the habitable zone, Earth's a good place to start. So when you grab a rundown, you'll have this section up here. You can just add, you know, information about your run if you want to, you know, if you're going to come back to it a year later and you don't know what you did. A lot of us, you know, do as I say, not as I do. We don't actually document well everything up here all the time, but you know, that's something you should do. When you grab a template, a lot of this stuff is going to be like source files that are needed, and usually you're not going to change a lot of these once you grab an appropriate template. The template it will vary if you have tracers, if you're doing a land planet, or, you know, whatever. But once you grab, you know, if you don't have a good template to work with, you can message us, but usually we have something that'll get you on the right start. But from there, most of the stuff you're not going to like change. You do have to have this, you know, I mentioned not Earth or anoxic Earth or whatever planet you're doing. That's you write it here. So I'm doing anoxic Earth, which is just an O2 free Earth atmosphere essentially. There's some other things that, you know, I added. You're not always going to see some of these like more clouds diags. This is just some additional like cloud diagnostics. Some of these aren't in most templates, but you can, you know, there's things you can add if you need them. Anyway, so yeah, for the most part, you'll just need to declare your planet name, anoxic Earth, for example, up here, and then we go down to this input file section, and this is, you know, we talked extensively about your initial conditions. The good news is, you know, we do have initial condition files for already for a lot of applications, and so you don't necessarily need to change these. You may, and it depends on what you're simulating. This is an aquaplanet, so these so this is your atmospheric initial conditions, and your uh, ocean initial conditions. So if I, let's see if I have one of these, I can just open up. I have my panoply open just to see what one of these looks like. Yeah, so this is kind of the old version of an OIC file where we have some obscure like potential enthalpy and stuff like that. But nowadays we can do in Planet 2, we can do just temperature and salinity directly. But when you open up these files, most of these are netcdf. It's pretty easy to work with, and you can just look at the field and plot these up in every. This is not a good plot, but so every grid cell or whatever will have some value for your initial conditions. You just want initial conditions that are like kind of sensible for your planet. If you change the atmospheric pressure, you'll want an AIC file that kind of has that kind of pressure. Your topography is going to be set in the well, you have the topo and topo OC files. Actually, it's one thing worth showing real quick just to show what it looks like. So this is, let's see what this one looks like. All right. Your topography files will basically have an ocean fraction. Actually, this is not a good file because it's. So I had one of these open and then I quit Panoply, and so then it disappeared. But oh yeah, so this is your fraction of ocean. So if you open that, you'll basically you'll have a map of zeros and ones. The topo file has an F ground, so that's like your fraction of ground, and Z ocean is your ocean depth. So wherever there's ocean, you can look at here it's 1360 meters everywhere where there's ocean. So that's where you set those kind of things if you're interested in different topographies, different ocean depths. It's just in those few files, topo OC, and this simulation's an aquaplanet, and then you'll just need initial conditions that are appropriate for that planet. So for example, you need salinity defined, in a grid cell where there's ocean. But all right, and then there's no shortage, vegetation. If you have vegetation, this is an aquaplanet, so this is just, it doesn't matter actually what this file is. But if you have land, you're going to want, either you could do a bare soil planet or whatever, but there's different options for your vegetation input. This doesn't have a geothermal heat flux, but there are input files we use for ocean or land geothermal heat flux. We could show you how to do that. But yeah, pretty straightforward. Your greenhouse gases are going to be set in this line. So this is just a text file, which looks. Why is this? Oh, I didn't even. The slash. Yeah, so it's just a text file with kind of, it looks like years, and then this is 1 ppm of CO2 and 0 other things like methane. We don't use CFCs really for exoplanets because they're anthropogenic. For Earth runs, this can be non-zero. The year will matter later. I'll mention when we get to the master year thing. All right, so that's a lot of what you set with the radius and the gravity and your atmosphere and your topography, all those kind of major boundary conditions. And then down here in the parameters, we're going to set some other things. We say this planet name again, anoxic Earth. And then Eric talked about radiation and what spectral file we used. For this Gliese planet, I didn't have that star exactly, but it was reported to be about a 3300 Kelvin star, plus or minus 50 degrees or something like that. So I used a 3300 Kelvin spectral file that we use that you know, should roughly correspond to this star's effective temperature. You know, if I was doing this for a publication, I would try to grab the actual star spectrum, but this should be close. And then you'll need a spectrophile, and this again, Eric talked about all the myriad combinations of things you could do. These spectrophiles for long wave and short wave are based on the star atmosphere combination. So you would need a different spectrophile if I was doing a super dense CO2 atmosphere or a hydrogen atmosphere. But these spectrophiles are fairly standard for like an Earth-like atmosphere, and then you just have to check that there's actual compatibility when you go to the spectrophiles folder and you kind of look under your star, which is this LTO33. You'll see what spectrophiles are available for different atmospheric possibilities for planets orbiting that star. I missed the first when Mike talked about the calendar. I'm sure he talked about you know, quantize year length, and this just forces a situation where there's an even number of days into the year. First, this is I'm assuming a synchronously rotating planet, so the orbital period and the rotation period for this planet it was 12 point something Earth days. So you just convert that to seconds and put that here. They're the same because I'm assuming it's synchronous. And the solar flux for this planet was 1.6 Earth value. So Earth is about 1360 watts per square meter. That's the solar constant. So multiply that by 1.6 and you get this. And so you put that down in watts per square meter. Just assuming no eccentricity, no obliquity, you can do whatever you want. There's a few other you know, possibilities as well with the orbit, the longitude of periapsis, which, you know, it matters if you have, you know, on Earth, it matters what if you know, northern hemisphere summer, for example, occurs when we're far from the sun, because we're tilted. But you could, you know, if you're doing a simulation for like, you know, 10,000 years ago or something like that in the mid-Holocene, the orbit will be a little bit different, and so you would change the longitude of periapsis. But that's not going to matter here when you have no eccentricity and no obliquity on an aquaplanet. So and then there's a lot of other stuff. This is actually in this version, I guess I have the dynamic. It doesn't matter. It's an aquaplanet, but you know, I'm turning off rivers, so it does it interactively if there is topography. And we have kind of things I just add to all my run decks now, which kind of we've learned through trial and error tend to help with bugs and stuff. Like just changing some kind of bounds for your min max temperatures, and ensuring you know, mass checks are and this is like a drag parameter. Just, you know, I just put these in all my run decks now, but anyway. Again, for a dynamic ocean run, you know, for if you're doing like a Q-flux run, this section is going to look different. But we have, you know, a dynamic ocean. You'll make a choice for, like, this is our mesodiffusivity constant. You know, you could change this, but a lot of this stuff you're not actually, you know, going to change. It's or you don't necessarily need to once you have a template. And then I used Mike doesn't like this, but I had showed you a 1 ppm in that GHG text file. I just multiply this by 300, so I have a 300 ppm CO2 atmosphere, which is kind of like Earth, you know, maybe, I don't know, 70 years ago or something like that. Now it's like 420. And then there's no methane, no ozone. You can you can also just put CO2 to 300 in that text file and then set this to 1. You know, it should give the same answer, however you want to do that. Just make sure you don't, you know, you don't double count and do like 300 here and 300 in the text file, because then you'll have a lot of CO2 in your atmosphere. So just be careful with that. And then you make choices for the time steps. I think this 900 and 225 is pretty standard in a lot of our, you can go, there's certain rules that need to be followed. You can do 1800, you can do, you could divide this by 2, like 112.5. If you're not sure, just ask us. But we have this new thing, well, it's not new now, but this equation of time, which it matters for, like, if you're doing weird, like high obliquity and kind of weird. This basically will affect insolation on some of these exotic orbits, because it affects the basically allows, like, the length. The equation of time corrects for, like, changes in the solar day, like, for example, on an eccentric orbit, when when the planet's moving at different rates around the star, you have changes in the solar day. The equation of time will, this gives more accurate results for, like, high obliquity planets, but the default used to be false or something. But anyway, just use true, because and then you'll have some other time step things, your surface interaction time step. I think this needs to be a multiple of 2. Sometimes you can get around some bugs if you increase this. NRAD is, we use 5 or 1. I don't know that we can do other options, but this is this is your radiation time step, and sometimes we go down to 1 if we're having some troubles, but it slows down your run too. So if you can avoid NRAD equals 1, then I think 5 is chosen because it allows, like, an even sampling of radiation. Someone can explain better, but it allows you to sample, like, radiation at every point in a coherent way.
Chris,
Yeah.
regarding NRAD, it is something that we have not focused earlier. So since you are chatting about that, NRAD is every how many time steps we call radiation. And then
Yep.
the reason why we chose 5 is not to have an even sampling, it is for having an uneven sampling. So that you will not be sampling, for example, every day for Earth at local time 1 p.m. and then you never sample the 1:30. It is so the model has 48 time steps in a day, and then you need to have essentially the number of time steps per day divided by NRAD should not be an integer. That's the idea. And then when you change the orbit, this 48 might change. And then if you have shorter or longer days, this might matter. But in general, you need to select something that will not create a sample bias.
Gotcha. Yeah. All right. Thank you. Yeah. So, and then there's choices for things you can turn on. Some of these will slow down your run. For example, a lot of times you want cloud radiator forcing diagnostics. You'd set that to 1, just like that. It just slows down your run because you need to call radiation more often, but that gives you some extra diagnostics as far as how clouds influence radiation. If you have aerosols in your atmosphere, there's similar flags you can set. Mike talked yesterday about this NMUN-AB, which is your this is how often your output files, like what the averaging period is, and so the default is 1 for monthly. 12 would give you annual output. Since this is a 12, and remember, it's not based on years, it's based on orbits, and so this is a 12 something Earth day orbital period. And so if you choose NMUN-AB 12, for example, you'll get 1 orbit or one Gliese 12b year every 12 Earth days. And so you'll basically have an annual file. Like, it'll eat up your disk space, because you'll have an annual file every 12 Earth days. And when you're running a model a few decades or a few centuries, usually to equilibrium, that's a lot of data. So for these short orbital periods, I usually choose something like the number of orbits in one Earth year, for example, which is, and then you have to make it divisible by 12 and stuff. So, you know, usually it's going to be a few hundred or a few thousand you could do, but you can make different choices. And then, yeah, and then you need this year I, year E. Just, you know, this would, you know, these numbers actually don't really matter unless you're doing, for example, like an Earth run. Oh yeah, I mentioned master year that I didn't get to. So, where is it? It's in here somewhere. Well, where's my master year? Anyway, 1850 here. But there's what's the flag for the transient? There's, if you're doing a transient run, it would have to be some something else. Costas, do you know offhand? I'm blanking on if you're doing like a transient.
Yeah, it's 0.
Yeah. Okay. Yeah. So it'd be something else. And then, you know, so the GHG file, for example, you know, it would have a time series of CO2 values. And there's equivalent things for other potential forcing terms. So for an Earth run, you need, you know, if you're doing a historical simulation from, you know, 1850 to 2000 or something, you need to account for the actual years. But for exoplanets, we usually don't do time evolving greenhouse gases, for example, and so you know, these years are pretty arbitrary. Yeah, I like to start with one, and you know, but you could do whatever. So that's the basics of a run deck, and now I'm short on time, so I'm gonna just show real quick. Once you get some output,
You have 20 minutes, Chris, 20 minutes more if you like.
okay. Yeah, so once you remember, I chose nmun of you know, whatever value it was, 300 something, and so I get my averaging period is about 28 orbits, which is, you know,
It's just one thing I wanted to mention, since you're talking about Rundeck. So since this aquaplanet that basically related to any aquaplanet, it was mentioned that with aquaplanet we always have to have an island on South Pole, just because our model is constructed, and that means that actually, though it's aquaplanet, your land specifications are not completely meaningless. Meaning that because one cell still has to run on land, you cannot do whatever you want. Like if you have some exotic planet, you don't want to have any plants there, for example. So whenever you model aquaplanet, make sure that you at least have only bare soil in your veg file. Otherwise, your trees will start dying because you have like 400 degrees Celsius temperature, and your model will crash for basically non-physical meaning, for not physical reasons, but yeah, just be careful that when you have some exotic exoplanet, put something reasonable into your land specification, just to make sure that it's something benign and you don't stress model too much.
fair enough. Yeah, so when you yeah, and so then once you'll do your run, which I'm not going to go over the commands now, but just, you know, once you get your run going, you'll eventually start you'll get some output. Again, I chose nmun ab of 300 something, and so I'm getting output at kind of like 28 orbits for this planet, which is, you know, it's a 12-day, so, you know, it's probably about an Earth year. Like 12 times 28, I think, is close to 360. So it's roughly an Earth year that I'm choosing as my output frequency. And then people, you know, we mentioned restart files yesterday. These are your kind of and you could remove some of these. You know, they can eat at disk space, but you know, these are, if your run crashes, you'll want an output restart files at some frequency in order to kind of start your model run from that point, rather than, you know, if you run for 200 years or something like that, and then your model crashes, and then, you know, you don't have a way to come back to it. All right, so the output are these ACC files, and we talked about the scale ACC command. So you would just scale ACC that file, and then you would do kind of whatever, so we talked about AIJ, that's your kind of two-dimensional like lat/lon variables. That's where a lot of your stuff's going to be, like surface temperature. If you want to do like in the AIJL is your, and so now these files are in the directory. And this the L is the vertical stuff. So if you want the three-dimensional atmospheric structure, you can also just do all. So if I do that, it'll give you a bunch of these possible things that a lot of which you'll never use. AIJ is the big one, but there's different. For ocean, you have OIJ. It's like, and then OIJL is similar to AIJL, except it's in the ocean. So now it's ocean lat/lon depth, and AIJL is atmosphere lat/lon height, pressure. A lot of these other things are going to give you, if you're interested in calculated general circulation diagnostics, for example, or transport terms. Very often you can look through these because they'll already be done for you. You don't need to calculate them yourself. So yeah, just explore like OJL, OTJ, AGC, some of these you'll already have, like if you want northward ocean heat transport, for example, I think that's in OTJ. So you don't need to like calculate it by yourself. Anyway, so once you have that, and I'll just show a example. So I already imported these files to Panoply. So that's the AIJ that my Panoply's been acting weird. I don't know. Okay, so this is that AIJ file that we looked at. There's a few things you want to look at right away. One of which is also, it's a good idea. We sometimes set, I mentioned this is a synchronously rotating planet. Sometimes you want to look at what's INC.
INCSW_TOA.
Yes. INCSWTOA, and you want something kind of like this. We could center it on 180 degrees. This is not a good color bar. You could, for incoming radiation, maybe something like that. But it looks like a synchronously rotating planet. Okay. These continents are just there's no continents on this planet. It's just a panoply thing. You could remove them. And yeah, so if you're doing a synchronously rotating planet, you're looking for kind of like this bullseye pattern that you expect on a synchronously rotating planet. If you find something that looks like a uniform, like, equator to pole insulation structure like Earth, then you did something wrong. It's just worth double checking this, because this is one of those things that, you control with the orbital parameters. We look for radiation balance, and so now I'll give you the conclusion about the habitability of this planet. This is where my Panoply's been weird. I can't actually like search variables. I don't know what's going on with it, but usually you can type in your variable and then like press enter and it'll like find it for you. But for some reason, this is not working for me at the moment, so I have to scroll. And T-surf is your surface air temperature. Now for each variable, we also have a HEMIS option, which is, well, it tells you the dimensions is SH/NH/GM. That stands for Southern Hemisphere, Northern Hemisphere global mean, and it's just 3 numbers. So if you click on that, you'll get the global mean temperature. Right now is 79 degrees. That's warm. But this is not an equilibrium. So you want to, the other thing you want to look at is, and this is warmer than we really even like to simulate with this model, but N comes before O, I think. Yes, that's how the alphabet works. You want the net red planet is your check for radiation balance. Remember, this is only, what did I do? I did we're only 250 orbits in right now, so this is not expected to be in equilibrium, even if it was a temperate, mild planet. But in this case, if you look at net red planet Hemis, this planet is 119 watts per square meter out of balance. So this is not going to be a habitable planet. This model is going to blow up. So so that's so if Gliese 12b is an aquaplanet or has a substantial ocean, then unfortunately all these headlines are wrong. This planet is going to run away. But usually when you do a simulation, your net red planet is going to kind of be large initially, and then it's going to decay to zero or something close to zero. And so if you run this, you know, for a few hundred Earth years, you're looking for net red planet pretty close to zero, and then you know, and then you can look at the climate during that time. But right now, yeah, this planet is blowing up, unfortunately. So that's what I get from that simulation. Some other oh yeah, and that's just the global mean values. If you want to make pretty maps of something like you know, T-surf, you know, you can use the panoply. This is net solar radiation, whatever, just whatever variable you want. You just make your map, and panoply allows you many options to make these plots look pretty, many color bars. Of course, if you're using Python or R or your favorite language, you know, you'll do netcdf operations there. But this is, I find panoply good just for, you know, especially one map plots or just like quick checks of some of these things. Yeah, so that's how you look at an output file. This is the AIJL version. Again, you know, this is your three-dimensional, like lat, ln, pressure. So you'll get things like this that are temperature, and you would change, for example, to latitude vertical, or this is synchronously rotating planet, so maybe longitude vertical, and then you would center on the equator, for example. This is, let's say, 23 degrees latitude. So this is or 23 index. So that's like in the middle. 23 is the middle of 46. So that's around the equator. And so now this is a longitude plot versus pressure, and you could do some better color scale and set your bounds and all of that. So you could see the temperature. It's, well, this is not, you need a color bar that looks, you know, but this is 180 degrees, right? So, you know, this is hot everywhere. But that's what the vertical structure looks like. Anyway, yeah, so that's how you would kind of get started, kind of looking at output. And I think I don't have anything more right now. If I missed anything super important, someone will let me know. And yeah, hopefully that's just a kind of a quick run through of how you'd make a new planet. And yeah, I think we have time for questions, but that, you know, you could do that. You know, I did that in like 15 minutes, just, you know, because, you know, we have templates that cover most of our grounds, and then you change your orbit parameters and your atmosphere and so forth. And then, yeah, and then you just let the model run. And then once, yeah. So, all right,
Great.
I'm done.
Thank you, Chris. Thank you. We could have a couple questions before we have our break and then go into the Q&A. If there's anybody that has anything really pressing they want to ask Chris, or we can just take a break and pick it back up. Silence will be taken as it's time for a break. Okay, great. So let's take a 20-minute break, roughly. We'll meet back at the top of the hour. And if you have questions, please put them in the chat in the meantime. We can get through those, or we can just have you unmute and ask your question when we come back at the top of the hour. Okay, thank you all. Okay, we are back for the last Q&A here. And we will hang out for as long, up to an hour as we need to. I see there is a question in the chat. Perhaps to Chris. Chris, we saw the geothermal heating in your run deck, but you didn't really describe it. We don't even know what units it uses. Are you there?
Yeah. Let me turn on the
Maybe you could
camera.
bring that up again and show what the units are, or tell us what the units are, because it didn't say in the run deck.
Yep, let me just make sure I have the right. So there's, I actually didn't include it in that run deck, so I'll write in the
In the chat?
It should be in words per meter square.
Okay,
Yeah.
Tony says it should be watts per meter squared, whatever units you are using.
Yeah, so there's two, wait, is that, did I get that right, geotherm? Yeah, and then there's, so that's up in the initial
You can also
condition.
provide a 2D map. What's the entry for 2D map?
So, so there's net CDF files, which is, so I'm writing in the chat just in case no one's looking there. There's geotherm underscore land, geotherm ocean equals, those are net CDF files. They're just lat lon, and they have units of watts per square meter. The geothermal flux is applied to the bottom of the ocean, or to or a flux from the land. It's not currently beneath ice sheets, but yeah, so that's how you'd implement it. And then there's scaling factors, which, so I like to use, like if it's uniform, you could actually just do like 1 watt per square meter, like as an input file. And then actually if it's uniform, I don't even think you need the input files. You could just set geothermal land X. But if there's spatial structure to the geothermal heating, then you need an input file, and then you could just scale the values if you desire. So
Sorry, so that wasn't
it.
clear. So the geotherm land X is a scaling relation or not? Because you said you could use it instead of a net CDF file. What did you mean?
If it's the way Rito Rudy implemented this, the way he set it up is if it's uniform, you can actually just not have the input
It's a run
files.
deck image.
But what is the run deck parameter? That's what I'm asking.
The name, you mean?
Yeah.
So if you don't define the input file, but you define the multiplication parameter, then the input file
It will be there.
is implicitly means 1, and then you use the factor. That's confusing. I think you should be using the file.
I agree.
All right. Well, you use the file. Yeah.
I mean, you should be using the file for your base case, and then use the multiplication factor if you want to explore the parameter space. But using only the multiplication factor is probably a bit sketchy.
I agree. So yeah, there's an input file up in the like kind of where you put your initial condition file, and then there's the scaling factors, these land X, ocean X, down in the parameter section. And so that's all you need is the input file, and then if you want a scaling factor, yeah, or you could just set it to 1 and then just use an input file.
But I think there is a run deck parameter to set a constant value.
Yeah, it's at least for the ocean, it's called F geotherm. I can put it in the chat.
Geotherm. Okay, for the ocean.
So if, for example, if you want a constant geothermal heating of 1 watt per meter square, you will just set this variable equal to 1 in your run deck. Okay.
Mm-hmm.
Great. Thank you for the question.
And that's another thing when you run like when you get output, just the geothermal heat flux will be in the diagnostics, and so just double check that it is what you think it is.
It's in the AIJ file, or where is it? How do you
It's
find
in
it?
AIJ for land, and actually OIJ for ocean, and it's called I think e-geotherm, let me just double check. I think it's e-geotherm over land, and then anyway, so if someone wants to ask a different question now, I will just find the variable name. Oh yeah, it's D. Yeah, it's this fucking weird thing.
Yeah, Steven's asking a question about optimal number of processors, and you discussed that a bit yesterday.
Before going there, let's go to, there's a question from earlier from Eric's talk.
Okay.
So Eric, you are here, right?
Yep, I'm here.
Okay, so the question was actually from Mariela right next to me. If you use a time-dependent stellar spectra, is it possible to calculate the shortwave spectral file with Socrates?
So Socrates does not support using a time-dependent stellar spectra because of the way that the shortwave spectral file is created. It weights within each spectral bin the contribution of the stellar spectra against the correlated K function for each gas, and that's done as a pre-processing step. So in order to rewire Socrates in order to take a varying stellar spectra would be a significant undertaking.
Really? And that
Yeah,
means
I
that
mean,
so we cannot use Socrates to run a historical simulation with solar cycle?
that's a good question.
Well,
Not
the
to,
spectrum
I
is
mean,
not
to my,
changing that much over the solar
It
cycle,
does.
only in the UV, not in the.
But it's important.
Yeah, but in the
Yeah.
UV, fine, yeah.
right. So that, yeah, that's an interesting question. I don't know. As far as I know with Socrates, I don't see how exactly that would be done. Maybe there's some special function that where they can, you know, I know with Wacom and CSM, they have special functions for stellar variability, which themselves are decoupled from the radiative transfer for climate, if you will, because as Mike said, it's into the UV. It's really you know, more of a chemistry, and in my knowledge, a chemistry focused endeavor with the Wacom when they vary the stellar spectrum for the solar cycle. Yeah, I mean, one would have to, because of, you know, how Socrates does it with embedding the weighting of the stellar spectrum in the spectral file. Yeah, you'd have to, yeah, it would be a coding project to try to pull that out and put in another mechanism where you can have that stellar spectra varying as a function of time. Yeah, I mean, it's a good question. Yeah, that's a good question.
Thinking out loud, would
Yeah.
one be able to simulate, let's say for the 11-year cycle of Earth, have 11
Yeah.
different files, and then implement some functionality in the model through the Rundeck maybe that says for, depending on the year, pick that file for Socrates.
So yes, that would, yeah, one could do that. One could certainly do that. That might be, thinking out loud, preferable to diving into the actual Socrates code and starting to monkey with what's going on in there. You could, yeah, I think that's a good you know, a good compromise solution that you suggest, Kostas.
Okay, thanks.
I mean, you could even break it down in even smaller chunks if you wanted, you know, month by month.
Yeah, I mean, it does, it's not a smooth function for when you change, when you have transient solar spectra for like this radiation, for example, it's not smooth, it jumps.
Oh, so yeah.
Yeah.
Okay. Do you want to cover the optimal CPUs question from Stefan?
I don't see it.
What's the question?
I see geothermal discussion.
205, you put the question.
Oh, okay, there you are. Yes, I see it. So optical number of CPU cores. So the model scales with the number of cores that you can use. So for the M40, the optimal number is 44.
For Socrates.
For Socrates is not separately parallelized from the rest of the model. So the model does the parallelization in latitude bands
Yeah.
and does everything for each one.
But I think that we have been able to run quite efficiently with 23 cores with the GIS radiation scheme and the M40 model.
I'm pretty certain that 46 will work better.
I'm sure it will, but I'm saying it works
Well-
pretty well.
well,
Yeah, 44, sorry.
It partially depends on what is taken most of the time. Is it column physics or is it dynamics? Because if it's dynamics, that it doesn't make sense to parallelize to like the highest resolution, because you will have one latitude per CPU per core, and that will not very efficient with dynamics, because there will be a lot of data exchange. But with Socrates, Socrates takes all the time that basically you can give it, so it's like, at least in my runs, it's usually like 95% of the time being spent in Socrates, which is column physics. So basically that means that you should use as many cores as you want, because data exchange between cores is negligible in this case. So in that sense, in Socrates, it's efficient to use basically 44 cores with GIS radiation, since it doesn't take that much time. You already spend a lot of time in dynamics, and dynamics is not very efficient on 44 cores. So you can go to 223 and you basically wouldn't lose that much.
Yeah, we did tests on Planet 1.0 with the E10N20 model, and 23 cores was very fast.
Sure, but was it twice as fast if you were going
No,
to
it
44?
absolutely was not quite as fast.
So that means that dynamics were taking more time than radiation.
No, you still will be faster on 44 cores. It's just like if you're asking, is it better to run like basically if you want to run one model on 44 cores or two models on 23 cores, like how it's more efficiently to use it, then yes.
It definitely was not a factor of two faster to double the number of cores.
Yeah.
Yeah.
It was more like 20%. It wasn't
Yeah.
worth it.
No, 20% is not worth it.
So
Well,
we
it
would run,
depends,
you can run 10.
Well,
you can run 10
it's not
models.
worth it. Wait, it's not worth it if there is a queuing system. But if the computer is all yours and you can use as many cores as you want,
Yes.
then there is no
If
reason
there
to
is a
delay.
system where you can use as many cores as you want, yes,
Yeah.
use as many cores as you want.
Yeah.
But I've never had such a system.
You don't use more than 44 cores.
Yeah, you cannot use more than 44. You cannot use 1,000. Yeah.
Okay, Stefan, hopefully we did not confuse you even more with our incoherent answer.
So with GIS 23, Socrates 44.
If you're using the 4x5 model.
Right.
If you're
4x5.
using the 2x2.5, the F fine resolution, then you double the number of cores again.
I mean, for the fine resolution, I always use 88, which is the maximum.
Yeah.
Oh, you can do 88?
Oh, of course.
With
Number of
188?
latitudes minus 2 is the hard limit.
Oh, okay. Okay.
Number of latitudes minus 2 is the hard limit,
Yeah.
as closest is saying. That's the
Yeah.
good
Okay.
barometer that we go by.
Okay.
Hopefully that was clear.
No, I would just like to speak up one more time and correct myself that, so I opened up the Socrates users guide, and this is the functions that we have not used yet, but there is a procedure for, as Kosta said, generating stellar variability around modern stellar spectral variability. So they do have a procedure set up. We haven't actually used it ourselves, but they do have a procedure set up similar to what Kostas was suggesting about putting in, sub steps of different weightings for the stellar spectra over the solar cycle. They have a procedure for that that can be run with their, the prep spec command and whatnot. So we just haven't done it yet. I know this came up in the context of binary star systems. That is another leap probably beyond what they're considering with stellar variability, because when you have a binary star system, as we've talked about, the stars can have such different spectra that you would have large changes in the weightings within the bins. But so yes, I have to correct and retract my last statement. They do actually provide some functionality for that, but it's not stuff we've explored yet.
Thank you
Right.
for reading the
Yeah.
manual.
Yeah, well, that's always what one should do first. Obviously, I didn't get to that, that chapter of it.
I guess for Planet 3, we will have that because it will need to be part of the integration of Socrates to Model 8.
Very cool.
Okay, should we go back to?
Yeah,
I guess-
Stefan has this question about the energy closure.
Yeah, can somebody like repeat it or?
Yeah, so his question is this. Looking at the energy budget for an ocean surface cell, for example, net radiation, sensible and latent heat from AIJ, vertical and lateral heat fluxes from OIJL, there is some gap to match the heat content of that cell. Could precipitation do the trick? And I said that it might be horizontal heat that is missing. So how do you close the budget in one grid box?
Well, I'm usually working with land surface, so it's a little easier because there is no lateral heat transport. So for land, it's pretty easy, but precipitation, as I mentioned in my email, it doesn't carry any heat as long as you don't change its phase. So basically, if it's a liquid precipitation, then it's zero flux. If it's also snow, then yes, snow brings in latent heat related to condensation, I mean, to freezing of liquid. So in general, I mean, if it's a warm cell, yeah, I guess it should close like net radiation, sensible heat.
Make sure, well, if it's covered by ACIs, you need to take that into account in your budget.
Yeah, well, the CIS is much more complicated because you have also water.
Yeah.
Well, again, I guess melting water is not carrying because it's at 0 degrees. Or it's not at 0 degrees because it's salty.
Yeah.
Yes,
Well,
I guess.
It might also be the case that we don't know exactly which diagnostic Stefan is pulling. So
Yeah.
maybe you could send us an email, Stefan, and tell us exactly which diagnostics you're pulling to make sure that you're using the correct ones. And then we can double check. And if you can tell us which run you've checked this on, maybe you could send us the netcdf files you're looking at, and we can double check that ourselves.
Yeah, if you are looking at a single cell with only liquid water, somewhere like close to equator, it's
I was going to
it's
say,
easier.
if it's a coastal cell and you have some river discharge.
Yes, also.
Yeah, I just wanted to say that if you're looking globally at the ocean, it's kind of tricky thing because there are a lot of things. Yes, there is water discharge from rivers and there is meltwater from ice. So yeah, and it's kind of not easy to figure out what is the heat flux from the ice. It's easier to treat ice as part of the ocean than it's kind of.
He said it's in the tropics. No, I know. But again, it depends if
Yeah.
it's a full ocean cell or not. If it's coastal, it could have some other components that make.
Well, he's talking about OIJL, which means that he's having dynamic ocean, so there is no partial grid box there. So even if it's a coastal grid cell, it will still be 100% ocean.
Yeah, but you could still have discharge from a river.
Oh, you mean for runoff?
Yes,
Okay, yeah.
but in the middle of the ocean, yeah, I guess. But
I guess you could have
honestly,
the GL melts.
I'm not very familiar with
Yeah,
what-
also,
what are
yes,
heat
also
flux,
could be the GL melt. That's another thing. So if you're.
If it happens to be in
If
that
your
grid
grid
box,
cell
yeah.
chosen is just where the GL melt array is overlapped, that could also cause.
Yeah, but also if you're considering only upper cell, then there is a vertical flux in the ocean.
Yes.
Maybe that's what is missing.
Could be
So-
also the
so-
bottom side of your cube.
Yeah,
You might have to consider that as well, Stefan. Yes, Kate.
Chris, when you were showing those run decks, I think for Tom Louisa, some of the comments for the like U00 A and B were mentioning tuning about high clouds and radiative balance. Is that?
You can ignore that. The template run decks are coming in balanced as they should, and then if you change the planet, you have no way to know how to constrain a newly balanced planet, so you're stuck with whatever run deck you start.
You don't want to play with
So
that.
But which means that you really need to start from a template that actually makes sense. Don't take, so you should make the least changes possible. So if you have a Q-flux ocean, if you want to use in your new planet a Q-flux ocean, take a Q-flux earth rounding. If you
Yes.
want to use a dynamic ocean, take a dynamic earth rounding.
And pick the
Right.
template
Pick the
from our
template.
list that's closest to what you want to do
Exactly,
in every
exactly.
case. And don't touch those. huge
Including resolution, atmospheric composition, everything. Just pick the closest possible and modify that, and don't touch the tuning.
Well, I'm not sure if that's what you're saying, that you're saying that you should use cloud parameterization, direct for Q-flux Earth, simulations, if you want to use Q-flux for.
No, they are not derived from Q-flux simulations. They are, all the tunings are derived by prescribed.
Yeah, that's right, yeah, so we always.
Yeah.
Yeah, so basically you should consider that, models like cloud model, it basically is tuned by running it for Earth. And once it's been tuned, you just assume that that's given, so there is no way to retune it for different planets, so you just assume that it basically works.
Because you
as
wouldn't
good
know,
as-
you wouldn't know what to tune it to. So
Yeah.
just
Yeah.
use Earth, that's all we
But-
have. Every model has this problem.
Yeah, but one should understand that tuning model for Earth simulation is also hack. Basically, your model should be good enough, basically just to work out of box. So if you have to tune it, that means that something is missing. So
Oh, yeah, it's, I mean,
Yeah,
that's
yeah.
why we have parameterizations,
yeah,
not calculations, yeah.
yeah, and also not every group is actually tuning clouds for basically to balance their model.
Yeah.
So that's just one of the approaches. So I can assume that basically clouds are given and something else have to be tuned. So. But basically, yes, don't touch those parameters.
Don't touch those things. Yeah. It's not a good idea.
So I have a question if there's not another one online.
I don't see any. I saw a question for Costas, but that's just.
So I had a question about the veg input file. So in there it has bright soil, dark soil, and then it has all the canopy types and all that stuff. It also has ocean in there. And I was curious
That's not
about,
used.
it's not, so that parameter
It's
gets
just got-
ignored.
It's some legacy
Okay.
garbage. Not
Yeah.
being used.
And so I also saw in some of the templates, it comments out veg. And so there's some default or something that it's pulling from, or
Probably question to Max, but a lot of things recently were made in such a way that if you exclude certain parameters or certain input files, then some default will be used. I'm not sure what will be used if you, I guess I never tried to exclude which file, but presumably it should be some bare soil. I'm just not sure which algorithm it will have.
It's easy to find out
I was
Run
going
it
to find out. on
and
my
look in the
Windows
partial
version.
file at
okay.
ground albedo, and you'll know what albedo.
Well, I know what albedo, I know what albedo it is. I'm just not sure where it's pulling it.
Yeah. If you're not sure, just check the output and see.
Like, yeah,
Yeah.
Even if you find the answer, it's better to double check that it's actually.
Yeah, my guess it would be either 0 albedo or maybe average, maybe like 0.25. That's
Yeah.
just to have similar fractions of the right and left. So
thanks.
Okay, so just to mention, Eric and Vincent are still online, so if you have questions for them, now's your chance. Or more questions for them.
We have a question for Vincent.
Okay, yeah.
When you were talking about, like 1D versus 3D radiative transfer, are you still, when you do 3D, like looking at like a single column as a whole unit, or are you doing like sub?
Is he here?
Yeah, Chris,
Do you hear her, Vincent?
was here.
He's not here. I'm sorry, he disappeared.
He was here like
2 seconds ago.
He literally sent an email 5 minutes, a message 5 minutes ago.
Okay.
Asking about. his
Sorry.
questions.
Well, when you see him, we can grab him. Or you can email him.
Hmm.
He's pretty responsive. We'll keep an eye out for him. Waylay him if he shows up. Sorry about that, Kate. Any other questions? Don't be shy. If there's something you're not sure about, please ask us, because if you're not sure about it, it's almost positive that someone else here is not sure about it as well.
That's another question.
Yes, please,
Yeah,
ask as many as you want.
You were showing some of the Mars cases earlier and you had the preprocessor flag about CO2 condensation.
Yeah.
Will that enable you to make CO2 clouds, or that's just interacting with the surface?
No, sorry, I didn't mention it, but we still don't have CO2 clouds. And it's still in the plans and
In the next version of the model, we expect them to be in there. It's under development right now. They're actually implementing it. We had hoped to get it in Planet 2, but our cloud guru did not like the cloud development in Planet 2, and he kind of revolted.
Referred to Planet 3.
He went to Planet 3, which he rewrote a lot of the cloud stuff for, and so he's much happier in that sandbox. Yes. No, don't say his name.
Sorry.
what I actually do have, but it's only, it's not included in Planet 2. I have precipitation, for CO2 precipitation, so it's still no clouds, but it's kind of still has effect on temperature of upper layers, because when you condense something, you change the heat content. But I was just doing some simple experiments with that theory. And if you're really serious about it and want to use it, we can discuss it. So it's available, but it's an experimental stage.
Yes, we're a typical modeling group. We're gonna have all kinds of functionality in the next version of that.
In a very next version of Planet.
Yes. Okay,
No questions?
no more questions. We get to go back to work. Okay, Stefan has another one. Oh, the South Pole land point, yes. Other than parameters for this. There's no weirdness. You define the topography yourself. So typically when we want aquaplanets, we set the South Pole topography height 0, basically. And often I just set it
Tony, one question for you.
to
Sorry.
Last question is for you. Last question. So, sorry.
yeah, anyway, yeah, we just set them to normal things. I mean, it's a very big, first of all, it's a very, very small point, the South Pole point. It's a very small fraction of it. So I think like you were
Yeah,
saying.
just set it to something reasonable. Yeah, zero height. Yes, topography is fine. 0 standard deviation probably is fine, but it's better to set it to something non-zero, just so that the PDL wouldn't crash.
I've set it to 30, and that seemed kind of reasonable to me, but more or less arbitrary.
Yeah, we have, I mean, we have run aquaplanet simulations, obviously, and if you look around and find a run deck for that, you'll find what we used. And since it's in there, that means it worked. So you can use whatever we use, Stefan, no problem.
Yeah, I guess usually I didn't hear from people complaining that the model was crashing there, but it's possible.
I've never seen an aquaplanet crash at the pole like that, but anything's possible with this model. It doesn't model after.
Yeah, but sometimes when people just model Antarctica for something non-modern Earth, then they have crashes there. So,
Sure.
so that's why actually I mentioned it. So it's kind of like small Antarctica. So.
Yes, there is development going on to change the mean molecular weight of the atmosphere as we move forward, but that would be, again, in the next version of the model. That's where all the development's taking place. Again, this is something we had planned to put in Planet 2.0, but simply we're not able to accomplish that because we didn't have enough horsepower, basically.
Yeah,
But that's
it's a-
being actively done in the next version of the model. I think it's actually working as far as.
Yeah, I think the claim is that it's already working in Earth model, so it's basically just so merging codes and. But that will be released definitely as Planet 3, not as Planet.
Yeah, it'll be in Planet 3, it will not be in Planet 2. Working as fast as we can. Never fast enough.
And the other question about dynamic land ice, we don't have that yet. And we really want it in the Earth model, so
But we've really wanted an Earth model for about 10 years and we have failed.
yeah.
So
and
we
now
can make no promises about when this might actually come to fruition, because the person that was most recently working on this left.
And the person that is now working on it is leaving.
Yes, exactly.
So we really want it. It's not yet
It's
ready.
a non-trivial development task, otherwise it
Yeah.
would have already been done.
Exactly.
That's what this amounts to. So sorry, Aaliyah, we're kind of stuck.
So when you say dynamic, do you mean, I guess I don't understand what you mean by dynamic.
The glacier to move, so you can have it calving properly, you
Sure.
can have, you track the mass of the water in the glacier. Right now it's a pit. And so you really track, you can create ice in a grid cell that the climatology would never do it just by moving it there. So these are the things.
Yeah,
And,
And also calculate the altitude difference from topography. It involves a lot of things.
and that happens within the time scale of the model.
Well, if you run it for 1,000 years, sure.
Sure.
Yeah, I don't think any 3D Earth climate GCM is actually doing full land ice dynamics.
Yeah.
Many people have talked about it. Usually what they do, Aaliyah, is they run the model to equilibrium, then they send it to a separate land ice model. They run that and then they ship it back to the GCM. It's sort of an iterative process. And Igor and I are also doing this for another project with a group in France. So unfortunately, that's how things are done these days.
But it seems like that's another issue where you're dealing with something that's on longer timescales than the model typically does, right? I guess that might be sort of a medium timescale one. I stand it.
Yeah, in theory, it is possible to implement something simpler. We have one developer here who actually does everything simple way. It's Gary Russell. So he has, I guess, has some ideas. Maybe he has even implemented
Probably in his model. There's a question
some
from the person.
basically land ice movement, but it's kind of like well, it's tuned to Earth observations pretty much. So I probably will not work well for exoplanets, but yeah, it has some simple model which doesn't like have real aeology, but basically just takes basically fluxes from observations as we know them. And, yeah, I think he did something interesting model. It actually is working. But right now we just have snow model which can accommodate snow, and you actually can use more than 3 layers. So in a sense, it can be treated as ice, but it doesn't move between the cells. So it's on the thermodynamics, but unfortunately no dynamics.
Is that related to why the default for the maximum, like, ice
Yes,
is?
Yes, so it's kind of like implicit way to model like ice dynamics, but instead of moving it to the next cell, we just dump it immediately to the ocean because eventually it has to go there.
Yeah.
So
Yes. Okay, no problem, Aaliyah. Okay, any other questions? Come on, Caitlin, you have a whole battery of them over there. Machine gunning us.
I guess I did have maybe a follow-up question on the molecular mass of the atmosphere. Maybe this is what you're saying is updated. Right now, does the model just assume that that's always constant? It
Yes.
doesn't- It just assumes the noise component is very small.
Yes.
Yeah.
Exactly right. And so typically, I think our former leader of this group used to say that as long as the specific humidity was less than 10% at the surface, it probably is accurate, but above that, he always thought that the convection probably would not be working very well because it's lifting, the mass lifting is different, is a different number.
I mean, the density of the atmosphere changes if you start taking that into account, and then it's, things happen that you should actually care about.
Well, the mass of the atmosphere itself also doesn't vary. So, I mean, the issue is it's, you know, the not just the convection, like the thermodynamics assumes water vapor is a dilute gas, which is it is on Earth. It, you know, it gets up to a few percent in the tropics, but the 10%, that was the number because Ray Pierre Humbert, he had this paper on like non-dilute, you know, atmospheres, and you know, he, you know, kind of argued for 10% as kind of when that dilute approximation in the thermodynamics starts to break down. But yeah, so
Yeah, but although Igor could point out that you can condense.
Yes, I mean, if you just, but it's different thing. I mean, just if you're talking about whole mass of the atmosphere, yes, you can condense as you do it for Mars. But again, in that case, we assume that the entire atmosphere is just CO2. Basically, again, we don't account for like small variations because eventually when you condense a lot of CO2, you actually start accumulating argon or other non-condensables. And we also have kind of unpublished, uncommitted algorithm which accounts for argon, but again, we don't take into account the change of in molecular mass of air. So we can compute the amount of argon which is accumulated at the pole. Basically, yes, enrich the poles when we condense CO2, but it's only in just basically dilute trace the amount of argon is created.
So it only works on Mars because it's a CO2, pure CO2 atmosphere.
Yeah, because it's like 95%.
Yeah, because CO2 condenses there.
Yeah,
Yeah.
right, yeah.
That's why.
And so your mean weight doesn't change.
Yeah, and
Just the
again,
pressure
I guess your argon can reach like significantly, maybe like from 5% to 30% close to the surface. I think that's what I was getting.
Also, regular weight of argon,
40. Actually, that's good because it's close.
Very close.
very close, 40,
Yeah,
close
yeah,
44.
44 and 40, so you can say.
40, okay, so yeah, that's really close.
Yeah, so it works basically.
Right.
For this case.
It works by accident.
Yeah.
You follow them.
It's even better if you have nitrogen and CO atmosphere, because both of them are just
That's
what,
perfect.
28.
That's perfect, yeah.
Farther down, farther down. Always in, it says one more. Click the red button. Which one? It's the overview road.
Oh, yeah, I got it.
Any more questions?
There's one
We
more.
still have 20
Tony.
minutes, we can spend them.
Yeah, it's the last one. This one again. We have different threads here. Have we answered? I think there's just one more for Tony, I guess.
Yeah, I think the other ones are answered.
Well, Caitlin, what's the other question you have? We're happy to have them, even if we can't answer them. Okay,
Oh, maybe how do you guys do initial condition file generation? You just kind of set like a guess from the equilibrium temperature, or do you do something more complicated?
yeah, I would say it depends. I mean, oftentimes we're just using Earth values that are in the model already. I think I mentioned for the Proxima run, I took an AIC file for Earth and I zeroed out the winds, for example. And that the model likes that more because it's just works out better that way. So often, you know, we try different things. But again, our recommendation always remains the same. If there is a planet you want to model, and we have modeled something close to it, find that run deck and make the modifications to that run deck and run that. If you want to run something that is very different from anything we've ever run, please talk to us first. Be a shame if you ran something that put out nonsense.
And it builds character to create new input files for a new planet.
Yeah. It took me a while.
It's not as simple as it sounds like,
Yeah.
hey, you take this topo file and you change the
I know,
topography.
that's why I feel like it's really good.
So it takes some experience for that, and
I mean, I think it's best to look at the current ones and understand them.
Yeah.
And then what I did in the beginning was I always took an Earth one, I modified it. And then I would compare it to the original Earth one, to make sure that the modifications I made were what I thought I did.
I think for simple planet, it's relatively simple. Well, I would, if you don't know, like, for where to start, I would recommend just to look at the simplest Mars run deck, because all input files are very simple there, and you can basically just look at any field. And I guess it doesn't have any reminders from Earth stuff, so everything was generated particularly for Mars. Well, except maybe roughness lens, which I think still uses Earth, but just one value from version from Earth. But anyway, at least there is no relation to Earth topography or anything. And unfortunately, I guess it's not documented, but it's more or less straightforward. I mean, what we did. The AIC file is pretty simple.
Yeah, I was gonna say, I don't. And maybe you guys know how, the AIC file is pretty straightforward. It's the winds, it's the water, it's the temperature.
Yeah.
More or less. And my intuition is just pick a reasonable value, zero out the winds, like Mike said. If you want to start with a dry atmosphere, do that, or pick a reasonable number.
I'd be careful about starting with dry atmospheres.
Yeah.
Sometimes they don't work very well.
Okay, I think I've always started with a dry atmosphere.
Put it
Well, it depends on what kind of planet you're modeling. If
Yeah.
if you're doing a dry world, maybe it doesn't matter, but if you have a
Sure.
planet with oceans, it's probably not a great idea. I've seen
Okay.
crashes.
For some reasons, my runs sometimes crash at the very top of the atmosphere when it's completely dry atmosphere.
But the atmosphere is gonna come into some sort of equilibrium or.
Yeah.
It's gonna change really fast versus like the GIC and the veg files, which don't change over time. Those are more important to consider, right?
GIC is also in initial conditions. And actually, my recommendation, if you can, don't use GIC file and use
Soil ice.
soil IC
Oh,
instead.
so I see, right,
Yeah, because GIC is a kitchen sink for a lot of stuff, even ocean, I think it's there.
yeah,
So it's an old file, and Max created much nicer system basically for each component separately. So like.
oh, so you can use it one or the other.
They'll overwrite, like if you use soil IC, we'll take the values from there, not from the GIC.
Oh, okay,
So for Mars, we use soil IC, which is very simple, as I was showing, just basically temperatures and the saturation level of soil.
right,
And you can just set everything with zero. Yeah, so snow is normally also set with zero because it will accumulate itself.
I had a question. This is
Sure.
about Celia. Hi, guys. This in regards to my run deck on Discover. So I know that back, I think it was a few months ago, it had did like a big update or something, or maybe the system was down. Because when I had one of my a few of my runs that I had going, they are now like converted to like .gz files where you have to like unzip them. And has anybody come across that error? Oh, I can see Mike's face is like, what?
Like, that's crazy.
Are you using one of ROCKE-3D's scripts for moving your output around?
yeah.
Am I using what?
If you're using those cron jobs that are moving things around, are you using those?
Yes,
Because
I
if
do.
you
have
do,
a
maybe
screen,
you've
yes.
used the wrong flag and that compresses output.
Okay,
Ask Reto.
okay, all right, I will ask
No.
Redo.
Do you know who Rado is?
Yes,
Okay, good. Ask Rado, but I think Kostas is probably right. It's probably a flag.
One of the flags that you've used is compressing, and I don't use them because I don't like things to be moved around for me, so it's, I don't know which one it is.
It used to be moved to the archive with a
Right.
Rito script, but since we don't have the right to write to the archive anymore, it's being compressed.
Yeah, so these are functionalities I don't use.
okay, I'll double check. Yeah, I was like, yeah, I haven't like updated anything since I had started using it back last year, so I was confused whenever I noticed that as soon as I started the runs, everything started to compress everything, and so I'll figure it out. Thank you.
Good question. Good luck.
Yeah, but that's not a model part, it's,
Yeah, that's,
it's still no.
Well, she started out saying it was discovered.
Yeah, so.
But there should be a command to like unzip those things, right?
Yeah, it's called gunzip.
Yeah.
Yeah, like I've been able to unzip them. I
You
just
can
noticed
do
that
it,
every
but
time
then
it restarts.
if your run
Yeah.
still runs, it will recompress everything.
Oh.
Yeah,
I've
it's
never used
recompressed
those.
everything.
Yeah, okay.
It's good. Okay. Any last questions? Another 10 minutes? Again, as we said towards the beginning of this tutorial, please write us if you have any questions. Sooner the better, because we're still in tutorial mode. In a few weeks, we will not be in tutorial mode and we may not answer your questions as quickly. So, people are busy trying to do their own science. Okay. Well, we will post these tutorial videos online like we have every other year. So if there's something you want to re-listen to, you'll be able to do so. And I'll send that link out to everybody, but it will also be put on the first slide of the tutorial slides that you have now. So that will be updated.
And we will put it over the also on Simplex. Actually, I'm not sure, did we ever mention the Simplex website? I guess.
There was a couple times, yeah.
The snapshots we mentioned,
Yeah.
the ROCKE-3D page, yeah.
Yeah, but the main thing is there is a ROCKE-3D page on Simplex website, and it has basically links to everything on
Yeah,
there.
also.
So
was
if you have searching for some information, that's a good place to start.
Do you want to put that in the chat quickly again?
Well, it's on the slides.
I know. It's good to
Yeah.
read it. Make sure we on the same page. Okay, good. Well, thank you all for attending. Really appreciate you joining us this year. We'll be back next year, so tell your friends and your frenemies. Come and join our tutorial. And you want to come in person, we consider that too. Yeah, okay, Igor?
Yeah.
Okay, maybe we leave it to the it's on the slides anyway. We mentioned that on the first day. Okay.
Yeah.
Okay, good. There it is. Excellent. And thank you all to our co-teachers too, very much. Okay, see you all later.
Right.
Bye-bye.
Bye.